Sir, Sankalp sir, shall we start the session?
Sure, sir. How
Yeah.
many participants we have got now
Uh,
so far?
right now we got around 40, I think. Yeah.
Okay, sure, sir. We can start.
Yeah. 35, 36. Okay, sir. So,
Yeah.
hi, good morning, everyone. From Chipin team, myself, Prince Henny. So, on behalf of Chipin team, I welcome you all to this day one of 3-day pre-event webinar sessions on digital design flow by Coral team as a part of Digital Design Hackathon 2025, hosted by Chipin Center, CDAC, Bangalore. So first of all, I would like to thank Coral team for accepting our invitation for conducting this pre-event webinar. And this webinar will provide essential guidance for upcoming digital design hackathon for all participating teams. From Coral team, we have Sankalp sir joined online. So sir will be the speaker for today's webinar. On behalf of Chipin team, I warmly welcome you, sir, to today's webinar. I would like to request Sankalp sir to take over the session. Over to you, sir.
Yeah, thank you, sir. Let's get started. Uh, Prince, is my screen visible? Is the slides visible?
Slides are visible, but it is not on full screen mode because next slide is also visible on the screen.
All right. Do you know how I can get out of this mode?
I think you have extended your display. That's why it is coming. If you remove that, it will come on full screen mode,
Okay.
I guess.
Is it okay now?
Uh, make it full screen, sir.
It's okay, I think, right?
Still not full screen.
How about now?
Uh, I think your screen got stuck. It got stuck, I think.
Just do
Can
one
you move
thing.
the slides? Hmm.
Okay, I'm just putting it to single display. Is it okay, sir, now?
Your screen, I think, is not stuck on that particular point. Can you move slides so that I come
Yeah,
to
yeah,
know
I'm
that?
moving slides.
But
I'm
it is
in
not visible
day.
here. Participants can also confirm if slides are moving. Because I'm not able to see the slides are moving.
How about now? Can you see my desktop?
No
Is my
desktop
desktop
yet.
visible? I minimized my PPT.
Or not here. It is not reflecting.
What is reflecting at your end?
The PPT slide, day one, designing with AMDP water tool. That is visible.
Okay. Just give me a few minutes, sir.
Yeah, sure, sure, sir.
Sir, I hope now my desktop is visible.
Yes. Yeah, desktop is visible, sir.
Okay, now my PPT is visible.
PPT is visible, sir. Go to full screen mode, yeah.
Okay, can I run it like this? Is it okay?
Okay, okay, fine, sir. You
Yeah,
proceed with this. Yeah,
yeah.
no problem.
So, okay, let's get it started. So, we'll have two agendas here, two focus for today's session. That is one thing is we are trying to understand this tool, how we are going to use AMD Vivado tool, and we are going to design some digital systems on top of something called the 7 series FPGA architecture. Okay, these are the two aspects we are dealing with. There is a tool. We'll explore the various features of the tool at the first level, and we'll build some small designs on a particular device. So that device is based on 7 series FPGA architecture. So one of the outcomes today would be like you have to understand 7 series architecture. So even participants should understand the various resources available on 7 series FPGA device and is in a position to predict what FPGA resources are utilized for small STL design. For example, like let's say you code something small as a 6 input AND gate. So this code is something that you write in Verilog or VHDL, but then on your FPGA device, what resource is being utilized, you should be in a position to predict. So there are something called LUTs inside our FPGA. Whatever we code, whatever digital designs that we have, they are mapped to these FPGA resources, right? So we should be in a position at the first step itself when we write a code that we can predict what resource on the FPGA we are going to realize. And participants should understand the usage of Vivado tool and is able to realize some small designs on FPGA. So before we dive into 7 series FPGA, because I understand that the background may be somewhat a little new to FPGA, let's take one step behind to clarify what is in fact inside a orthodox, very traditional FPGA. Then this becomes very easy. What is inside 7 series FPGA would become very easy. So now my next few minutes are going to make you understand what a bit stream is. At the end of this, let us say 10 to 15 minutes of discussion, you would understand what bit stream is. Okay, yes, sir.
ಆಲ್ರೆಡಿ ಎಲ್ಲ ಮಾಡಿದ್ವಿ.
Is there a question for me or kindly mute if there is no question? Okay, let's proceed. What does the most complex digital circuit comprise of? So I have everything listed here, but this in fact maybe even for simplest circuit. You would have logic gates like and or not. Also any boolean function can be implemented. You would have flip-flops. You would have wires to connect all of them. So complex digital circuit comprises of all these elements. Now, this is what we would have seen in our third semester or in our textbooks, right? On a digital design course, you would start off doing some combinational circuits like half adder, full adder, ripple carry lookup adder, so on and so forth. And then you shift to sequential circuits where you look at flip flops, latches, and then counters, then some FSM, so on and so forth. So basically, at the bottom, everything is implemented using these kind of circuitry only. But then these circuits do not exist inside my FPGA straight away. They are going to be mapped to FPGA resources, in fact. And the FPGA resources are what we are trying to understand in this first session. So for this complex digital circuit realization, we could go two ways. Either we could go the ASIC way or we could go the FPGA way. What I've highlighted in red is the FPGA way is what is going to be our focus in the next 3 days. So it is possible to reconfigure different functionality even after manufacturing by reconfiguring this internal hardware resources. So as I'm saying, FPGA has some resources, right? So maybe once, to make it a simplistic discussion, maybe first time on you want a 6 input AND gate, right? And your FPGA is implementing a 6 input AND gate. Then next time on, maybe you want the same device to be doing some kind of a image processing algorithm. So you are able to reconfigure a different functionality altogether on the same device.
Sir,
But whereas
your
ASIC,
slide have been stuck in first slide itself.
okay, now how about now, sir?
No, sir, it's
Are
Sir,
you
it's
only
still
stuck
the
in the
same,
first slide.
sir.
now? Now is it moving?
No, no, sir.
I put it in PPT mode. Is it moving?
No, sir.
Not yet, sir.
I haven't shared the entire screen. Okay, I am again going to stop sharing.
Sir, you share the entire screen. I think
Yeah, I've
then
shared the entire
problem
screen,
will
sir.
not come. Yeah.
I've shared the entire screen only. Now you're able to see, right? You're able to see my desktop and you're able to see the WebEx.
WebEx is visible.
Okay, now my desktop is visible.
Yes, sir.
Okay, how about now? Are you able to see complex digital circuit
Yes,
realization?
Yes,
yes.
sir.
Yes, yes.
Okay, I'm going to put it on slideshow mode now. Now, how
Yes.
about now?
Fine, fine, sir.
Okay. Okay, so ASIC is in which the functionality is already implemented at time of manufacturing. Once you manufactured that particular device, the functionality cannot be changed. Now let's focus back on this FPGA aspect. See, here you say, look at this word reconfiguring. So little bit loosely we use that we are programming our FPGA. We are not in fact writing a C code on an FPGA, rather we are reconfiguring the hardware resources to be implementing different functionality. Let's proceed. So here actually I am going to be looking at the more traditional FPGA. So field programmable gate arrays, they were semiconductor devices that are based around a matrix of configurable logic blocks. So they are itself called programmable gates, right? Connected via programmable interconnect. So this picture speaks a lot about what is inside a traditional FPGA. So let's think of this as a 1985 FPGA. So inside this, you see these gray blocks. They are called your configurable logic blocks. And then you see these programmable interconnects. So I have a spec. Let's say I want to come up with a digital circuit. So that digital circuit, I would have written a Verilog code or a VHDL code. And finally, there is a process to be followed such that internally to these CLBs, some configuration happens and that functionality is realized along with the programming of the switch matrices. So effectively, this is going to implement that particular digital circuit. So that's the switch box for you, and this is the CLB. It is possible to implement different functionality in same FPGA by changing CLB contents and routing logic. This is called FPGA configuration. So around this FPGA configuration is what we are going to be talking about bitstream. There's something called bitstream that is going to do all of this configuration. So let's understand a very essential element that is inside our CLB. Inside the CLB, there is something called a lookup table. Now, for the first few minutes, I'm just talking about the 1985 FPGA architecture, not the 7 series FPGA architecture. LUTs are essential elements of CLBs. So let's say a conceptual discussion about how an LUT can implement a two-input AND gate. So this is the truth table of a two-input AND gate. And how is it that I configure my CLB in order to implement a two-input AND gate? So this is what existed inside my CLB. So inside this gray block, traditionally this kind of a structure existed. There's a lookup table, there is a D flip-flop, and there is a 2:1 mux, and that's the select line of the mux. Now the task at hand is to make this CLB work as a two-input AND gate. So just a while ago, I've shown you that this is the input, this is the truth table of a two-input AND gate. You will have to feed the output column of the two-input AND gate into this lookup table. So you would be feeding in 0, 0, 0, 1. So this is a two-input bus. As of now, let's say that A and B are my inputs to the lookup table and Y is the output. So whenever A, B is 0, 0, this is a conceptual discussion, right? The 0th location is selected. At 0th location, I have 0, and that is going to be placed on this line. Whenever I have 1, 1 on this line, I mean this two input line, then the location number 3 is selected and 1 is placed on this line. So going from 0, 0 to 1, 1, you can select any of these entries, and the output is going to be the corresponding output of your AND gate truth table. Now you have a whole lot of blocks, right? You have a mux in on the way, you have a flop on the way. You only want to make it work as a two input AND gate. You would not like the flop to be on the way. In that aspect, you need to select this select line as 0 so that this path is taken, so that D flip-flop path is not taken. So in fact, the configuration bits or the bit stream configuration bits for this CLB to work as a two input AND gate is going to be if I may say 0, 0, 0, 1, which is talking about the 0, 0, 0, 1 that sits here, and the select line that I'm going to be selecting as 0 to be taking this path 0. So this is the bit stream configuration that is required to configure this CLB as a two input AND gate. So implement two input AND gate, assume LUT with two inputs. So implement two input AND gate whose output is registered. So now I want something which looks like this. I want AND gate whose output is going to be registered. That is my spec. Okay, this is the circuit I want. So this I'm going to configure 0, 0, 0, 1. So the configuration bits are going to be 0, 0, 0, 1. But I need to have the flip-flop on the way. So I need the flip-flop on the way. So I need this line to be activated. Hence I need to select 1 on the select line. So in fact, my bit stream configuration for this circuit is going to be 0, 0, 0, 1, 1. What about this circuit? In this circuit, I have AND gate followed by a flop, followed by an XOR gate. So in the current architecture, which is of the CLB, which is this, I will be requiring two CLBs. And this is my second CLB. So I need to configure CLB1 with a particular bit stream and CLB2 with a particular configuration bits. So what is going to be the configuration bits for CLB1? For AND gate, it's going to be 0, 0, 0, 1, and I need to take the flop on the way. So I need to have the select line as 1. So that's 1. As for XOR gate, the XOR gate truth table is going to have an output column which is 0, 1, 1, 0. And I don't want the flop on the way, so I need to be taking this line. So I make my select line 0. So 0, 1, 1, 0, 0. So that is as far as the CLB configuration goes. But what about the connection? What about the connection over here? There's a connection that needs to be established, right? So for that, there's a concept of switch box. Let's think of a switch box which looks as 6 pass transistors connected like this. So I need to make, let's say that this is my CLB1, this is my CLB2, and suppose that the routing has to happen through this switch matrix. So basically I need to make this connection. So I'll have some numbering for these with pass transistors. So I'll call them 1, 2, 3, 4, 5, 6. Okay, and let's say I want to make a west to east connection. West to east connection. So if I numbered the transistors like 1, 2, 3, 4, 5, 6, then only transistor number 3 has to be on. The remaining transistors have to be off. So here you have the remaining bits over here, which is talking about the configuration for your switch matrix. So I believe it is 0, 0, 1, 0, 0, 0. So just for this small circuit which is here, this small circuit which is AND gate, flop, and XOR gate, the number of bits if you count are 1, 2, 3, 4, 5, 5 plus 5 plus 6. So 16 bits for this simple digital circuit. And our FPGA devices are going to be extremely rich in FPGA resources, and we can realize more and more complex digital circuits, right? So with this background, let us actually see what is inside my AMD 7 series FPGA architecture. We don't have a 2-input LUT that we've been talking about. Rather, we have a 6-input LUT. When I have a 6-input LUT, you can realize any 6-input Boolean function. So how many rows in the truth table? There are going to be 64 rows. There are going to be 64 rows. So this Y column is going to be 64 rows. That means your lookup table, if I'm going to visualize like this, it has 1, 2, 3, 4, 5, 6 lines. So A, B, C, D, E, F are talking about your inputs. Y is talking about the output of LUT. And there are going to be 64 locations. Conceptually, there are going to be 64 locations. So you can realize any 6-input Boolean function. So the 7 series FPGA, what it contains inside CLB, it is not only about LUTs, it contains other resources as well. And it's not just 6-input lookup table, rather it is 4. We have 4 6-input lookup tables in each slice, in fact. So let me make a comparison between 1985 FPGA versus 7 series FPGA. This is my 1985 FPGA CLB, that gray block. How is it different now with respect to the CLB? Each CLB contains something called slice cell and slice cell, or it would contain slice L and slice M. Just hold on. What is inside this slice L? What is inside one slice L? You have 4 6-input lookup tables. You have 8 flip-flops. You have something called a carry logic, which is nothing but an implementation of a carry look-ahead logic. You have some multiplexers to cascade logic. How is it different from this guy? This traditional CLB. Traditional CLB had just one two input lookup table, it had one D flip flop, and it had one 2:1 multiplexer. Rather now, one slice, only one slice, not even two slices, I'm talking about one slice, is going to have four 6 input lookup tables, eight flip flops, a bunch of multiplexers, and a carry lookup logic kind of block. But inside a CLB, you can have two slices and have two slices, which is slice L variant of a CLB, or you can have something called a slice L slice M. So this is a CLB now, and this is also another variant of a CLB. So what is inside? What is inside a slice L is what I'm seeing here. I have four, 1, 2, 3, 4, 4 lookup tables, 6 input wide, the multiplexers, one level of multiplexers is there. This is my carry chain block, and these are my 8 flops. This is versus my 1985 traditional FPGA. Only one lookup table, one flop, one mux, bunch of multiplexers, bunch of lookup tables, a bunch of, that is to be precise, 8 flip flops, and one carry logic. Slice M also looks very similar, right? It has four 6 input lookup tables, the same levels of multiplexers, carry lookup logic, and your flip flops. But the difference, if you observe keenly, is you are going to see that the number of inputs on the LUTs are going to look a little different. And that's the reason why it's called Slice M. It has capability of realizing memory structures as well, small memory structures as well. These are for logic, right? These are for logic. Like you can implement some Boolean functions or some combinational circuits using these LUTs. But an LUT inside SliceM, not just the Boolean functions, but also you can implement the LUTs as memories as well. So when you have memory structure, you will have clock, you'll have address bus, you'll have data bus. All that is accounted for by the extra lines on these blocks. How many LUTs do you think are needed to implement a 8 input Boolean function? So our LUTs, our 7 series LUT has six inputs. So 8 input Boolean function, I would at least need 2 LUTs. And of course, I would need a extra level of multiplexer to do some kind of cascading. Okay, so the answer for this would be 2 LUTs, 5 input OR gate. I can implement that using 1 LUT. So these are the various variants of devices in my 7 series. Going from left to right, the number of logical resources as far as proportional to CLB goes, it increases. You see in a Spartan 7 device, these are the logic cell range: Arctic 7, Kintex 7, Vertex 7, and Ring 7. So all these, one needs to understand that these are one category and zinc is one category. So I'm putting this category over here. If I put this as a block, like an FPGA device, either Spartan 7, Arctic 7, Kintex 7, or Vertex 7, they are what is called as pure FPGA devices. So what is spread inside this block, inside this device, is what is called as PL, programmable logic. A whole bunch of things like CLB and other resources, right? So that you can implement your digital circuits on FPGA. That's all that your FPGA can do. But when it comes to zinc, you have what is called as the PS side of things. You have also what is called as the programmable logic. So if you wish to implement only FPGA, you are only working on the PL side. But if you want to have a processor and work with some kind of logical blocks, and you want to build an embedded system. So when you want to build embedded systems, you would need this entire zinc kind of a device, and you would have a processor, and you would have some kind of accelerators that sit on your PL side to implement an embedded system. So you will have to write a C code, an application code, which coordinates the activities of your embedded system. So that's the one difference. As a beginner, one should know that your FPGA provided by AMD, one is the pure FPGA, which is talking about all of these, and one is the Zinc, which is a system on chip, which is a SoC. So how many LUTs are available in Zinc? So roughly, I mean, this conceptually, it's going to be into 8. I'm taking this number 28,000 and I'm multiplying it into 8, right? Because I have one slice which has 4 LUTs, but in one CLB I have 2 slices. So I have effectively 4 plus 4, 8 LUTs. So you can understand that just this LUT, 6 input LUTs, this is a big number, right? I can achieve a whole lot of a big complex digital circuit realization is possible. But other than CLB is what is available. There are other resources as well. There's going to be DSP slices, there's going to be block ramps, there are going to be high speed serial transceivers, there are going to be XADC blocks. So using all these CLBs and all of these, you will develop digital circuit implementation. So basic elements at the block level inside my 7 series FPGA would have all this: CLB, block RAM, DSP slices, transceivers. These are to get it to the outside world. Okay, IO to get it to the outside world. So we had seen only one row talking about logic cell range. So this is a chart which gives us, in my 7 series FPGA, going from Spartan 7, Artix, Kintex, Vertex to Zinc, how the resources got scaled up. What are the number of resources? That is what this slide is telling. So we have block RAM, we have DSP slice. Here the performance of the DSP slice is given as you go across on the various devices. The number of transceiver blocks, transceiver performance, memory performance, number of IO pins, the voltage level that is supported. Now the question is, I have a 7 series device with a whole lot of FPGA resources. How is it that I can implement hardware on these resources? The hardware that I visualize may be some kind of a image processing algorithm that I want to implement, right? How am I supposed to implement it on these FPGA resources? The answer to that is, we will follow an FPGA design flow. Early on today, I was showing you how do I realize 2 input AND gate, like the bit stream, right? We were telling it is 0 0 0 1 followed by 0. I mean that bit stream, I'm the configuration bits, I'm building up towards that, right? It's not possible for very complex circuit to come up with this mapping. Maybe in the early days, maybe they would have done this, but then we later on the FPGA design flow got evolved, and you need to use FPGA design flow. What is the first step in FPGA design flow? You have a spec, and that spec you've got to map it onto a VHDL code or a Verilog code. Okay, so that gets us to the Vivado tool basic flow. So let's say that my intent here is to realize a 6 input AND gate. So you'll write um, a module in Verilog. So this is describing the name of your module. This is describing the inputs and outputs end module. So that's a black box entity level. In VHDL you may say, in Verilog you say it is module. It's a black box. You have not yet told what is the functionality of this. So you have to describe the functionality by some statement. So we are doing assign y, and we are writing this statement, and that is going to implement a 6 input AND gate for me. Now I am not going to be writing the bit stream, right? So FPGA design flow has to come up with a bit stream. How does the FPGA design flow come up with a bit stream? What are the steps that have been followed? So on my tool, which I'll be showing you very shortly, we come up with a Verilog design file entry. So tool has to support a RTL file entry. On top of that, you do a behavioral simulation and verify the functionality of your code. And once you confirm that your code is working well, only then move forward in the flow. So design elaboration is a step wherein your code is mapped to a gate level netlist. Gate level netlist means something which still looks like your AND gates and OR gates and maybe flops, so on and so forth. Something that looks like your logic design um, course circuitry, right? Whatever you saw on your fundamental logic design book, right? The combinational circuits, sequential circuits, all or mux, you may see at this level, but nothing about the resources that are available on FPGA. When I come to synthesis, in fact, it's a mapping of this gate level netlist to FPGA level resources. Now, the FPGA resources, let us say, I am needing two LUTs, maybe to implement a Boolean function, right? Only two LUTs are needed, but in my Zinc device, there were a whole bunch of these CLBs. Out of so many thousands and thousands of LUTs, I need two LUTs. Who is going to decide where those LUTs are and how they are going to be placed? That is being done by at implementation step, where the actual placement and routing is completed on the device, followed by bitstream generation. And through hardware manager, then through hardware manager, you are going to be sending in the bitstream to be configuring your device. So I'm going to be talking about pin constraining on the demo. Okay, just hold on for a bit. So let's look at tool snapshot. We start with design file entry, and then we do a behavioral simulation on top of that. We do design elaboration where you see a gate level netlist. Please note that though you have coded for a 6 input AND gate, maybe what you visualized is something like this. But our tool gives us the functionality as described with these 5 2 input AND gates, and it very much implements the functionality of a 6 input AND gate. After synthesis, this is a 6 input AND gate. It can be easily implemented using a 6 input single LUT structure, right? So this is the FPGA level resource that is required to implement 6 input AND gate. With the truth table of this, the truth table of this is configured as a 6 input AND gate. And obviously you have these input buffers and output buffers. So these are your FPGA level resources. So after implementation, your See, all these are CLBs. These tiny blue structures that you see over here, these are called your clocking regions. So if you see x1 y1, x0 y1, x0 y2, these are all your clocking regions. We'll get to that, but you should understand that all these regions have CLBs and other resources. So out of a whole lot of area, only this place your tool has identified to implement your 6 input AND gate. Let's take a zoom in on that. So you see that there are 6 inputs and 1 output, and this is your 6th input LUT. So bit stream generation and hardware configuration. So if I look at a zinc device, what I wanted to say is there is one side of it called the PL side of it, and the other side of it which is called the PS side. So PS side is where you are going to be configuring your hardware resources, and whenever you use your PL, your PS, you are planning to use an application code and coordinate something on an embedded system, right? But for today, sorry, this is PL. For today, we are going to be staying on the PL side of things only. So with this, let's get to our first demo on a 7 series FPGA device. So I want to keep things simple. So I'm going to be using a pink Z2 board on which there are two dip switches. So I want to utilize the two dip switches, and I'm going to have a single output which is connected to LED. So that's the naming convention. Two inputs of my AND gate and one LED. So yeah, the digital circuit that is being implemented is extremely simple. The idea here is to understand the Vivado flow. Okay. So we'll start by creating a project. So I'll give the name. I can give the same name. So we will select it as an RTL project, and we are not going to specify any sources at this time. That means that I'm not planning to uh, have a file loaded into my Vivado right at this time, the RTL file, right? I'll do it later. Then I select board, and I'm going to select my pink board. Okay, this is called a flow navigator on my Vivado tool. If you remember a while ago on the slide, I've shown you that the first step in my FPGA design flow is to have a Verilog file entered or a VHDL file entered. So this is the place wherein you will be adding the source or creating a source. Then this is the place where you will be running the behavioral simulation on top of it. Then synthesis, and then implementation, then bitstream, then hardware manager. So let's start by adding a source. So I'm going to add or create design source. So again, remember this. I'm taking this specifically a simple example just to go over the tool flow. So let's say that there are two inputs. I'm going to say A, B, and Y is my output. So I'm going to have assign Y is equal to A and B. Let's look at in design elaboration what it's going to map to. What we are expecting is in fact a two input AND gate. So I open elaborated design and I look at the schematic. So this is what you could also do when you're doing a more complex circuitry as well. When the spec is more complex, you at this stage you could very well go and see what schematic is coming out of the elaboration. So elaboration is a step wherein your code is getting mapped to a gate level netlist. So I've opened elaborated design. So you see elaborated design is open and I'm going to look at the schematic. So in fact, it says RTL AND, two input AND gate. Now let's explore behavioral simulation side of things. So I prefer to often close a given design after my job is done on that. So I would recommend that you could run synthesis, you could run implementation also with this open, but I prefer to close a particular design when I plan to go to the next step. So I am going to close the elaborated design and let's look at the simulation. You see only behavioral simulation is highlighted. That is, I am going to check the behavior of my code. I am going to verify the functionality of my code, whether it works as per two input AND gate. And I'll explain these in a while, what these are in a while. These are not highlighted because I'm still to run synthesis, I'm still to run implementation. So let's run behavioral simulation.
Excuse me, sir.
Yes.
Sir, while installing the Vivado software for select editor, we are getting like two options, like to install standard or enterprise. Which one should we install, sir?
One standard enterprise Vivado installation.
Standard.
Standard
No,
installation.
just a minute. Okay.
Okay,
So
sir. Thank you,
you
sir.
are just a minute. You are installing Vivado or Vitis.
Sorry, sir.
So we have one is embedded application also, that is Vitis. So we'll encourage you to install the Vitis entirely. Okay. So when you download it, the installer, okay, from the AMD Xilinx to this one platform. So you will be getting one tool, Vivado tool installer, right, for Windows application or Linux, whichever it is. You download that. When you are going to install, no, it will ask for like you whether you wanted to store it for the afterwards installation or on the fly you need to install it. There are two options will come. Okay, so you have to select the afterwards so that you can install it in multiple PCs. So once that install like entire package is downloaded, it will be around 25 to 30 GB package. Once it is done, then you can install that. In that you are going to install the Vitis part. Once you install the Vitis, then as well as a Vitis, that is embedded platform. So now, sir, what is covering is on Vivado Flow. Maybe in coming like the next session, so maybe tomorrow or day after, so we'll be covering few of the embedded concepts also, which requires both Vivado as well as Vitis. So kindly download in such a way that.
Okay, sir. Thank you, sir.
Yeah.
Okay, let's proceed with the behavioral simulation. What I'm demonstrating here is what is called forcing, right? I'm not writing a test bench. I'm going to be forcing values because this is a two input AND gate and it's quite easy to look at all the cases. But eventually there is a requirement for a test bench because what happens when our design has more and more number of inputs? It's not possible to force all these values, right? So for a simple design, I'm demonstrating the forcing way. So I force constant 0 0 and I run it for 50 nanoseconds. I say 0 0 is 0, then 0 1 is 0, 1 0 is 0, and 1 1 is 1. So this is my waveform. So right at the top of the flow, I just entered a Verilog file, two input AND gate. I ran the simulation of it, which is called behavioral simulation. So we are understanding the flow properly. Okay, though I have selected a simple design here, I'm again repeating. We will go in the Vivado flow as much as possible to the greatest possible extent with this. So I entered a design source using this, and then I ran behavioral simulation. I verified. Now let me run synthesis. See, I'm showing it to you as a step-by-step approach, right? But eventually we will not look at all this. Once you are confident and you have verified it, you could very well run bitstream, okay? And then make intermediate checks also. That is also fine. So first time on, I'm going step by step. So let's run synthesis. So synthesis has started. So this is showing which design run is underway. It shows synthesis is in progress. So once synthesis completes, you will open synthesize design. As of now, it does not show because synthesis is underway. Once synthesis is complete, once you open synthesize design, you will say open schematic. And what you see there is the connection of your FPGA resources. Now there is a 6 input LUT that is involved, and LUT is an FPGA resource. At elaboration, you see a gate, a 2 input gate. So synthesis is done. So open synthesize design. And let me open schematic. So it's a, what it is saying is it is a 2 input gate and there are input buffers being used. You could also report utilization on a very complex circuitry, and when you want to get insight into what are the various FPGA resources that are being used, you could say report utilization. So as of now, there is one 6 input LUT that is getting used. Okay, the naming convention is 2 because 2 inputs, right? How many slices were used? One slice is used and 3 IOBs are used, 2 input buffers and 1 output buffer. So basically 3, 1 slice is used. Now if I go back and look at my simulation, the run simulation, I will be able to see that I have something called, because synthesis is done, post synthesis I have some simulations which I can do. These are called post synthesis functional simulation as well as post synthesis timing simulation. When I'm talking about functional simulation, the tool is not going to consider the propagation delays of these buffers and these LUTs. But when post synthesis timing simulation is being considered, also some estimated values of these routes and estimated values of these LUTs are being considered. So we'll take a look. So see, this has got activated because I completed synthesis and I could do verification. I could do the simulation on top of this netlist. Now this is a synthesized netlist. I am running a post synthesis functional simulation. So it is also giving me the a I buff. This is the output of input buffer, okay, and this is the output buffer of Y, right, for the Y signal. So again, very quickly I'll do this. Finally, 1 1. So you see over here that things happened instantaneously. There is no propagation delay for the LUTs and input buffers. Whenever, yeah, if you see here, everything is happening at the same transition, right? Let us look at the same thing with respect to the post synthesis timing simulation. Okay, the number of signals look exactly the same. So I've given 0 0 0 1 1 0 and finally 1 1. See, when I've given 1 at the input port 1, there's already a delay because of the input buffer. So there's a propagation delay, right, because of the input buffer. For B also there's a propagation delay. So propagation delays are coming into play when you are doing timing simulations. So this aspect you could never explore in your behavioral simulation. First of all, in functional simulation also the timing was not being considered. The propagation delays were not being considered. So this is to be understood. Now you are going to see that eventually, after you complete your implementation as well, which is not done right now, you have a post implementation functional simulation, post implementation timing simulation. Now what is the difference between these two simulations? Here the propagation delays are estimates, but here they are precise. So you will see the actual numbers. So the actual waveform, the timing waveform that you want to see, if you want to see, you want to go to that micro level, then you would have to use run post implementation timing simulation on your complex designs. I am demonstrating again, reiterating that this is a simple design, right? But you will be able to see you would be able to appreciate that the propagation delay and the precise propagation delay, because routing has been completed, placement and routing has been completed after implementation. We'll close synthesize design and let us run implementation. So out of a bunch of thousands and thousands of LUTs, the tool is going to pick on one specific LUT, that is the process of placement. It's going to say that my design has to be placed over here in this LUT, and this is how the routing has to be completed. So this is what is going to happen after implementation. So routing is underway. The design is being routed for. So a while ago on the slides, I've also shown you something called pin constraining, right? So this is that aspect I kind of left out. So I could complete that pin constraining point apart after implementation as well. Let's open implemented design and let us go to device view and see where the device is being placed. So you have to go to netlist, you have to expand all the leaf cells. It's placed over here in this. See, it could have been placed anywhere, but it got placed here. The reason being some default pins were selected. And this is something that I have not specified. So the tool took some default value and the tool has decided to place my design close to the pins to whatever value by default it has picked. Okay, let's zoom in and actually see what is. It's a 6 input LUT itself. Whose 2 inputs are being used and 1 output is being used. Now for the constraining. So for the constraining, you would require a master XTC file. So I have already Googled for Pink Z2 master XTC. This is the first link that I've opened on GitHub. So my 2 inputs of my AND gate, I am going to give to dip switches. So I'll search for switch. So it is M19 and M20. Okay. And it is LV CMOS 33, low voltage CMOS 3.3 volts. So that pin which is being connected to the dip switch on the board is operated at 3.3 volts and has LV CMOS technology. So basically M19 and M20 pins on my FPGA device are connected to the dip switches on the board. So M19 and M20. And I am going to select it at LV CMOS 33. What about the LED? R14. There are 4 LEDs on my board. R14 is the package pin that I need to connect it to. And LV CMOS 33. So this is the graphical way, the GUI way of doing things. So I have done it after implementation. The same process can This you can think of it as pit stops. Okay, this pin constraining that I'm showing, which can be done after design elaboration, can be done after synthesis also, or after implementation also. And if you are an expert with tickle commands, or not such an expert also, you can just pick these commands from that XTC file that I've just shown you on the browser, and you can have a pin constraint file right at the top of your design in the first go itself. That is also possible. But at a beginner level, you can always open the elaborated design, and you can, like whatever I did now after implementation, exactly same thing you could have done after design elaboration or after synthesis. So this I need to specify to my tool as my pin constraint file. So I will go to file and I'll say constraints and I'll say save. The tool will prompt me to load this constraint into some kind of a file. So which is called a .xtc file. So I'll name it accordingly as pins because I'm doing the pin constraining. The package pins M19, M20 of my FPGA device are going to be connected to the two dip switches on the board, and R14, the package pin on my FPGA device, is connected to LED on the board. This information I got from my XTC file, master XTC ping Z2. So let's close implemented design. And now since I have changed the pins here, so the device, the implementation of design can happen in some other portion of the device. Okay, let's see that. Before that, let's see whether my constraints got updated or not. So under my constraints, I have pins.xtc. As I mentioned, after writing your codes, you could always say constraints. You could add a constraint file and you could write a command like this as well straight away. First step, you could do this. This is possible. Or you could always do it the GUI way. Now let us run implementation. Take a while. We're going to be running synthesis and implementation. So now this time after implementation is done, we will also go and see what happens after post implementation timing related simulation. Okay, this is something very interesting to note. Though I am looking at a 2-input AND gate, let us see if we are having favorable output results. Right, I selected a 2-input AND gate because it's a simple circuit, and you would all be expecting 0 0 0 0 1 0 so on and so forth, right? But is it what happens on my implemented after implementation when I'm verifying my post implementation timing simulation? So last step here, the design is being routed. So implemented design open, and this time on we'll see which portion it's implemented. Last time without pin constraining it got implemented in this region. See, now it's implemented over here. Your pin constraining is also deciding the placement, right, and the routing. Again, it's a two input LUT itself. Let's look at the schematic. Schematic should look the same. Here you have the truth table also. You have truth table. You can look at a truth table as well. So this is something that you did not specify, right? You have just written the Verilog code, but the tool is telling that this is a two input LUT. I mean, this has to implement this kind of a truth table. Now let me go to the post implementation simulations. I'll not run the functional simulation because again on functional simulation there is no concept of propagation delays. Let's look at post implementation timing simulation. So 0 done, 0 1, 1 0, and 1 1. Okay, this time I was not able to observe it, but on some of the circuits it's possible to see some spikes. On combinational circuits you can see some spikes, small signal going up like this. That's because of the propagation delay. The signals don't change exactly at the same time that you are expecting, right? There's a small delay in this. Because of the propagation delay there could be some kind of a spike. Hence that AND gate with flip-flop, AND gate registering is what would do a good job at implementation. You would not see spikes at this step. Okay, let's proceed. So implementation is done and we are ready to generate the bit stream. I'll just turn on the camera on the board. So bitstream is generated. We'll open hardware manager, which is going to coordinate bitstream getting onto your FPGA device to configure your device, right? Say open target, say auto connect, and I say program device. Now there is this bit file, the bit file that talks about configuring your hardware resources, FPGA resources on this FPGA device. So you can observe when you are able to see the board, right? Board is visible. Can I get a feedback from someone if the board is visible?
Yes, sir, we can see.
Okay. So when I program, you should be able to see that this done bit just started glowing. So your device has been configured.
But
Any issue?
sir, it is not the main screen. We can see as your display image of with your name.
No, I'm sharing a video that I'm able to see.
Oh, yes, sir.
When my screen is
We
when
can
this
see your screen as well.
no, now you can see my screen, but when I take off this screen and I go to Vivado, are you able to see the board now?
Sir, I can share a.
Is the board visible?
Sir, it is visible as a very small image on top. I can send you a
Okay,
screenshot.
okay, that's okay.
Fine.
What I wanted to say is you can see a yellow dot, right?
Yes,
You
sir.
can see a red dot and you can see a yellow dot.
Yes, sir. Yes.
So when I did the programming, this green light has started glowing, saying that the programming is complete. Now these are my dip switches, and there's a LED over here, and this is just a 2-input AND gate. So 0 0, the 1 1. When I have 1 1, do you see that the LED has glown? Can I get a yes? Is it visible?
Yes, sir.
Okay. So this is just a brief demo to walk you through the Vivado flow. Okay. Now let us, because on the agenda we should also understand the resources in a little bit of a detail. Let me demo to you some more things. So I'm basically, since the agenda is like if I run this is a 6-input AND gate. Okay. What is your expectation? What is the outcome? How many LUTs will be implemented? How many LUTs will be implemented? So I'm asking you a
One, sir.
question. This is one LUT. Okay, then
Yes.
this is a 7-input AND gate. How many LUTs will be implemented?
2, sir.
2 required, sir.
Two required. Okay. This is a full ladder code. How many LUTs will be needed to implement? How many? How many LUTs will be needed to implement this?
2.
Yeah, that's the answer I'm looking for, because we are a little bit confused at this point. So let me go back to a slide and just depict what is our understanding as of now. Visible? PPT is visible, no?
Yes, sir.
Okay, so what I'm planning to implement is a full ladder which has A, B, C, N. A, B, C, N. Some output and C out output. So at this point, what we believed is my LUT is 1, 2, 3, 4, 5, 6, 6 input and 1 output. So the answer so far what you have given is absolutely right with the knowledge that you have, because you would have told that I have three inputs, but then I have two outputs. So it's not possible to implement in this. Maybe I need one more LUT, right? But no, in fact, the
So like in
internal
this multiplexer
implementation of
and
this
can enter.
LUT is internal implementation of this LUT is slightly different, such that I have something called O5 and O6 outputs. Okay, and let us say that y1 is a function of ABC and y2 is a function of ABC. It is possible to implement both these functions in a single LUT. Not only ABC, if I have A, B, C, D, E, up to 5 shared inputs. A, B, C, D, E. So let's confirm this on the tool since there is a doubt. So I'll just make a modification in this. So we don't need XTC. So I'm going to delete it. This is a architecture level description. We'll see how this is getting mapped to a single LUT. So I'll run this only up to synthesis, maybe up to implementation to make you more convinced. Let's run up to synthesis and see what we have on the schematic. We will also look at the truth table, what truth table is being implemented. So if you have the tool with you ready, and if you want to run some things on your side, I'm also going to be sharing something. So bitstream is something that is used to configure your device to be working at a particular functionality, right? So let me look at the schematic. Okay, this LUT3 it says, and it says LUT3. It looks like they are two separate, right? But it's not the case. You may get a illusion that they are two separate LUTs. So let us to avoid any doubt, let us also report utilization. Let's see if we can get any input from that. Slice LUTs, how many is being used? It says one LUT is being used. Now let us actually run it to implementation and appreciate that in fact indeed it is one LUT. So if anyone is you running this code, you can run it up to implementation straight away. It'll just take a bit because some codes we are running to be appreciating the 7 series architecture, what is inside CLB. So as of now, we know that there is a slice L and there's a slice M. So right now, what is inside a slice L, I'm exploring through these small code snippets. And we will consolidate this understanding through slides in a while. Okay, so let's look at the schematic. Schematic looks the same. Okay, so you are not convinced now. Let's look at the device view now. Here you see that it's a single LUT itself. A single LUT has a O5 and O6 output. In slides, I'm going to explain that in a bit. This O5 and this is O6. Okay, let me reopen the tool. The next upcoming code is a code which looks like this. I'm going to run it all the way up to implementation and see what is being implemented. I'll select the pink board, sorry. Just call it adder. Yeah, let's run it all the way up to implementation. Any guesses? This may be too early on to make a guess, but still, I am also sharing this code. If anyone is running this, you can run the simple code snippet all the way up to implementation and realize, look for yourself what it's implementing. Anyone can make a guess as to what this code might end up inferring, what FPGA resource. As of now, what are the FPGA resources in my 7 series architecture as far as CLB is concerned?
Lookup table max.
Yeah, let me go to that window. Yes. This is my slice L, slice M. I have so many LUTs, I have mux, I have a carry chain, I have flip-flops, right? Now the code is adder code that I've run. What do you think might get implemented? I hope some of you have the tool and are running it. So the routing is underway, almost done. Implementation is going to complete. Any guesses? You can put it in the chat before I open implemented design. Anyone has a guess as to what this can infer? I have also shown you the slide with what resources are available. LUTs, multiplexers, carry chain, and flip-flops. Okay, let's take a look. We can report utilization to take a quick look as to what resources it has used. It has used up to eight LUTs. Let me put it up on the device view. See, what I wanted to demonstrate over here is, since I'm doing an addition, the tool has understood that you intended to do an addition and it is using CLA, the carry block, to do a fast addition. See, this is your carry chain block, right? And what is to be understood that whenever there is a carry out of this carry chain block, it runs vertically upwards. It's running vertically upwards. There is a carry out of this also, and it is running vertically upwards. So because I'm specifying to the tool that I intend to do addition, it is using a carry chain block. So you have to understand that as a FPGA designer at coding, what resources your code is going to go and hit. Okay, so you should aim at that level of understanding. Now for the interesting multiplexer. Okay, quickly before you can see the notes over there. So I'm going to be typing in a code for a multiplexer. This is the code for my 4:1 multiplexer. 4:1 multiplexer. Any guesses as to what it's going to realize? Someone can unmute and speak up. So as of now, we understand that in my slice L, there are going to be 6 input LUTs, 4 of them. Then there is multiplexers by themselves, right? There are a few multiplexers that you've seen. Then you've seen some carry chain block, and then one level of flip-flops, 8 flip-flops. Now what is this code going to map to among them? Any guesses? I hope someone can put it out in the chat if you're not muting and saying it out aloud, unmuting it. I have written a code of a 4:1 multiplexer. What will it get mapped to?
So it's multiplex.
Yeah, that would be the natural way of thinking, right? There's a multiplexer, it will map to a multiplexer. But then can you tell me,
LUT.
see how many inputs are there to this? To this multiplexer, how many inputs are there? 1, 2, 3, 4, 5, 6. 6 inputs and 1 output. This is basically 6 inputs and 1 output. So basically this is a Boolean function only, right? The implementation. So it will get mapped to one LUT. This gets mapped to a single LUT, in fact. So let's observe that. We'll run to synthesis. I'm just sharing the code. If anyone is, Govardhan Reddy gets it right. It's one LUT. So I have some interesting cases coming out of this multiplexer itself. So I'm sharing the code. So we will tweak this and we'll make it eventually 16:1 multiplexer, 32:1 multiplexer, and then I'll ask you the same question. So after synthesis, if you observe the schematic, in fact, it is a 6 input lookup table. The LUT 6, 1, 2, 3, 4, 5, 6, 6 input LUT with 1 output. So no need of running it up to implementation. It's very clear at this stage. Now I make it from 4:1, I will make it a 8:1 multiplexer. So 7 down to 0, 8:1 multiplexers. Number of select lines is 3. 210 the select line. You can make this change and run it on the tool and run it all the way up to implementation this time. So anybody now as to what this will implement? You just make this changes over here. You can share the code, new code one more time if you want to just pick it up. So could you answer? For 8:1 multiplexer, what are the resources that I'll be realizing? How many inputs are there in this 8:1 multiplexer? There are going to be 8, 9, 10, 11. 11 inputs, right? So how many LUTs I will be needing? How many LUTs I will be needing? I will need at least 2 LUTs to be implementing this. But then I need to cascade that. Then I'll be needing one level of multiplexer as well. So I'm expecting 2 LUTs and 1 multiplexer to implement this. Routing is almost done. Yes. Let's open implemented design. Look for report utilization. How many LUTs? 2 LUTs. How many muxes? 1 mux. Totally 1 mux was being used. Let's see that on the device view. 2 LUTs and 1 multiplexer got used. Now I increase this to a 16:1 multiplexer. So 15 down to 0 and 3 down to 0. With this, please guess. I think now you are in a better position to guess what is the resources used on my device. How many? I'll just share this code. If you could modify it yourself as well. Yeah, I think someone had a question or someone was giving an answer. This is a 16. Okay. Is it only about the LUTs or there are some multiplexes also being used? Yes.
Salam ini. Sarangnya bang Kevin ini.
If you don't have a question, please mute.
Kan? Saya jaga.
So totally how many inputs are there? There are going to be 16, 20 inputs. 20 inputs. So all 4 LUTs looks like we'll see. But some level of multiplexer is also being used in this. Almost done. This report utilization. This is F7 mux 2 is being used and F8 mux 1 is being used. On the slide, these are the F7 muxes and then this is the F8 mux. So all 4 LUTs, hoping that it is all sitting in one slice. Okay, sometimes tool doesn't do a good job and it might get spread out also. But if it has done a good job, it will all sit in one slice and it will use 2 F7 mux and 1 F8 mux. Okay, on the implemented device view, let's see. The tool has done a good job. It has utilized 4 LUTs. These are your F7 muxes, 2 F7 muxes and 1 F8 mux. Okay, with this, we have understood, we got a feel about, okay, in slice L, we have 4 LUTs, we have some multiplexers. These are called F7 multiplexers, these are called F8 multiplexers, and carry chain block. And if you code for flops or latch, it's going to come and sit in this resources. So I think I'll skip that section. So if you write this code, okay, let's just complete one flop. Okay, for completion's sake, I'm just coding one single flip flop. So this is a simple D flip-flop, D input clock and Q output. On the rising edge of clock, D goes to Q. This statement, positive edge of clock, indicates to the tool that you have to infer a flip-flop. If you would have given always at some signal level, then it would have gone to a latch. So let's run up the implementation. So this is going to be the end of slice L related discussion from tool point of view. We are yet to consolidate all of this on slides, telling that what are there inside LUT, because when we were talking about a full adder with two outputs, sum and cout output, we were a little bit confused whether it is going to go as one LUT or two LUTs. The answer was one LUT, right? So we need to look at the internal architecture of LUT and understand it a little more. So if I have to consolidate about slice L, there are four LUTs which are six inputs, which have six inputs each. Then there is two F7 muxes, there is one F8 mux, there is one carry chain block, and there are 8 flip-flops. Right now we are running the code of a single flop. So we would see that one flip-flop is being realized. After this, we go to the discussion on slice M. The slice M resources are exactly the same, except that the LUTs have more number of inputs in order to enable memory realizations, small memory realizations into these LUTs. Let me highlight all of them. See, out of 8 flip-flops in that slice, only one flip-flop got used. So that's about the architecture of 7 series from point of view of the LUTs, F7, F8 muxes, carry chain block, and the flip-flops. Now let's consolidate it on the slides. The slide is visible. Can someone read out to me what is on the slide? I hope I am audible.
Yes, sir.
Okay, my slide is visible.
Yes, sir.
Kindly give a feedback. Okay. So right now we are just revisiting the CLB architecture. We have already understood most of it on the slides, on the tool rather. So what is inside my 7 series FPGA as far as CLB is concerned? So here on the circle is shown like an FPGA fabric. Okay, the one that I open on the tool, right? that it is dense. It is showing that it's dense and there are a lot of FPGA resources. And then there is an expansion, and then it is showing that there are two slices. This is a concept level block diagram. There are going to be two slices. There is a switch matrix and there is fabric routing. And can someone tell me what is the C in and C out into this entire slice? What is this C in and C out talking about? The C in goes into something and C out comes out. What is this? What is that block inside the slice that is going to be taking the C in and give out C out?
That carry element.
Yes, yes, yes. So at this point, a simple block is given saying it is slice. What is the internals is not described. C in comes and C out goes vertically upwards. I demonstrated it on the tool, right? So CLB contains two slices, slice L and slice M. Carry chain runs vertically in a column from one slice to one above. CLBs are arranged symmetrically, and this improves density and improves routability. So FPGA slice resources, specifically slice L. Slice L, L stands for logic. Slice M, in addition to logic, it can also implement memory kind of implementations. So 4 6 input lookup tables, you call it wide multiplexers. You had F7, two F7 multiplexers and one F8 multiplexer, one carry chain block. There are totally 8 of these elements, of which 4 are purely flip-flops and 4 can be used either as flops or latches. The implementation tool is responsible for packing slice resources into the slice. So a while ago I said, right, I have a code and I hope that this multiplexer which is using 4 LUTs and 2 F7 mux and 1 F8 mux goes in one slice. That was my hope. But then implementation tool is responsible to take it up and actually pack it up in that slice. So the tool did a good job on, so whatever I thought was correct, and correct meaning the implementation tool did what was expected. So 6 input LUT with dual output. This was a situation when I was looking at the full ladder. So though I visualized initially the grand visualization that saying that okay, this looks like the 6 input LUT looked like this. At a box level, 1 2 3 4 5 6 6 inputs, one output, 64 locations internally. That was to just tell you conceptually. Internally, the implementation is rather 5 LUT implementation, and then there is a mux to take the output. So this is how we could implement a full adder which has two outputs. And if you observe here, there are 6 inputs, out of which 5 are shared among these two LUTs. So hence I can implement y1. Let's say y1 is a function of a, b, c, d, e, 5 inputs, and y2 is also another function of a, b, c, d, e. If I write a code for this, it will all go and sit in one LUT only, because internally LUT is implemented like this. So this is talking about the multiplexers. These are the F7, F7, 2 F7, and this is F8, F8 mux. So we also observed that F7 mux combines the outputs of two LUTs, can implement a 8:1 multiplexer. We observed this on the tool. F8 mux combines the outputs of two F7 mux, and we observed that we could implement a 16:1 multiplexer. So mux output, this output can drive out combinatorially or to flip-flop latch. Basically what they're trying to tell is You can take it out as it is, or you can register it. And this is talking about the carry chain block. Whenever we are trying to write a code to do addition at a high level, like doing y is equal to a plus b, where a and b are, let's say, 10 bits wide, then carry chain is being utilized. And important thing to note is the carry in comes here and carry out goes out like this, and it vertically spans through the device, goes up through the device. So here these flip-flops are pure flip-flops, and here these 4 flip-flops can be used either as a latch or a flip-flop. So what is important to note here is, if you write a code to implement a latch and this got implemented as a latch, then the tool is not going to pick this for flops. Okay, it is going to, if these flops were already used, if you had written code for a flip flop and these latch were already in, these flops were already inferred, if suppose this one was latch, the tool is not going to fit in a flop in this, it is going to go to another slice. Another important thing to know is, the at the architectural level, you don't have set and reset separate for the flop. So whenever you code, it is important to note that if you code in such a way that you have set and reset for the same flop, then some additional logic needs to be used so that set and reset is selected appropriately, because there is only one pin which can implement set or reset. So if you write one code to use a D flip-flop with reset, it is going to treat this as a reset pin. If you write a separate code for set, then it is going to use the same thing. But if in the same code, if you write set and reset, then more combo circuits or LUTs will be implemented to make some selection for this. Okay, I'll just quickly take a break of few minutes before I proceed to slice M. Okay, we'll break for lunch by 1, but I'll take a break of just 2-3 minutes and come back. Okay, we'll start the session. So in slice M, if you'd observed early on, you look at a comparison of both of these, you see effectively the structure remains exactly the same, just that the LUTs look a little different. And that is the feature of slice M, because you are going to be implementing memory related resources on these LUTs. You could also use logic, but this is specifically intended for memory related resources. So let's say that this is an LUT, right, which is 64 locations. So if I write a code for a RAM which is 64 locations deep, 1 bit wide, it is going to fit into one LUT. This is what we will observe. Okay, let me pick a code of a BRAM, or rather a LUT related RAM. So we are going to slice M related resources. So I am picking a code which is, I'll just run over the code. I'll just modify in the same project. So SP means single port, 64 locations deep, 1 bit wide. Okay, this has 64 locations. I'm planning to implement a RAM which is 64 locations deep and has data width of 1 bits. So there is a clock input, there is a write enable input, there is a DIN. Please observe that DIN is 1 bit, so I have not given this as a vector. But then to address these locations, to point out to the 64 locations, I have this address bus which is 6 bits wide, and I have output which is D out. So here I am describing, I'm declaring that there is a register memory which is 0 down to 63. Always at pause edge of clock, if write enable is high, then you write into that particular address which is pointed. Otherwise, asynchronously, you are always reading out. So this is an assign statement. Doesn't matter whether I have it here or have it down. These are concurrent. This always block versus this assign statement, they are concurrent. So if you observe, I have not put this D out inside this. Rather, I put it outside of this always at pause edge of clock. So one thing to note, important thing to note is we have made the read operation for this memory asynchronous. So this is an indication to the tool to put this memory into LUT. Okay, please note that the asynchronous read operation, which is not inside always at pause edge of clock. I could have also said else d out is mem of address, right? I have not done that. Rather, I made the read operation asynchronous. With this, when I run it up to synthesis, let's first run it up to synthesis. And observe that it is going as a LUT, 6 input LUT, which is being realized in a slice M. Hope I'm audible, right? Okay. So we are expecting the code that we have put to get into a LUT. Let me report utilization. It says 1. Slice LUT 1. It says 1. LUT as memory, it is 1. This code has mapped to one LUT which is used as memory. That's what the utilization report is telling. Let's look at the schematic view now. So this is in fact a LUT itself. The reference name is given as RAM S64E. So 64 locations, 1 bit wide. Okay. Let's once appreciate it in implementation. Now the next question to ask you is, if this code is going to sit exactly in one LUT, how should I tweak my code such that it utilizes all the 4 LUTs in one slice M? Let me put that question. Let me put the code as well. So this code that is put out in the chat box is going to go and occupy one single LUT. What changes do I need to make to this code to fit into 4 LUTs of a slice M? Think about that. I'm just going to check whether this is mapped to exactly one LUT, which we already have confirmed anyways, but on the device view, this is our memory and reference name is RAM 64. 64 locations, one bit wide. Now the next question I'm asking is, if I have to make this 4 LUTs occupied, what is the change I need to make to this code? Anybody? You can give your answer in the chat box. I posted the question. Anybody? So this is 64 locations, 1 bit wide. What is this also? This is also 64. This is 64. This is 64. So how much deep is this? 64 into 4 is how much? It is 256. So if I realize a memory 256 locations deep, 1 bit wide, it has to sit in one slice M. Provided the tool does a good job of packing it up into one slice. Okay, every time I'll give that disclaimer. So I'll just modify it to 256. 256 locations deep, 1 bit wide. So there are 256 locations, 256 locations. Address width should be how much? Address width should be 2 power 8 is 256. So 7 down to 0. So I am expecting that 4 LUTs in a slice M are going to be utilized for this. And with that could be the multiplexers as well. So after synthesis, we look at the schematic. Let's open synthesize design and let's report utilization. It says 4 LUTs and 2 F7 muxes and 1 F8 mux. How many are used as memory? 4 LUTs are used as the distributed RAM memory. Why the word distributed RAM, I'll give it in a bit. Now I'm opening this to show you that whether it's sitting in one slice M or it is spread out. See, it is nicely sitting in one slice M, 4 LUTs, implementing 256 locations deep, 1 bit wide RAM with 2 F7 muxes in the first level and 1 F8 mux in the next level. Now still it is not justified as to why it is called distributed RAM. You have made it tightly sit in one slice. Okay, a lot of routing resources are not being utilized for this. Let's make this a memory which is 256 locations deep, 8 bits wide now. Can someone give me an answer as to how many LUTs will be needed upfront before I run any code? Let me put the question out. To realize 256 locations deep, 8 bits wide. Memory with asynchronous read. Please remember, when I make my read asynchronous, it is going, that is the important takeaway from this discussion. Whenever I make my read asynchronous, I hope I'm audible. Whenever I make my read asynchronous, only then it is going into LUTs. With asynchronous read, how many LUTs are used? Please give a thought to that. Any answers for this? "256 locations, 1 bit wide" was 4 LUTs. So how many LUTs would I need right now? Just scale it up. Yeah, good answer. We'll check. Because 256 1 into 1 4. So if I scale it up, then it looks to be 32. We will check that. So I'm just changing the code. You realize that writing a code is not about just writing a code. You should also visualize what are the resources coming out of it. So I make 256 locations deep, 8 bits wide. So address is fine, but then my D in and D out also has to be changed now. Input is 7 down to 0. Output is also 7 down to 0. So this is a pretty small memory, right? 256 cross 8 is a pretty small memory. And what would happen now, because I'm implementing it on the LUTs in Slice M, they are going to get distributed onto my FPGA fabric. Slice M, there are multiple Slice M because it cannot, it just has 4 LUTs in one Slice M. It has to search for a more number of LUTs from another Slice M to implement this wider memory, right? So it gets spread out and it gets distributed. Hence, whenever I'm using LUTs, they are called for memory realization, they are called as distributed RAM. That is a point to be taken. The other important point from this discussion is this read operation is asynchronous, not made with respect to clock. When you code it this way, you are telling the tool upfront that you want to infer the FPGA resource, which is slice M LUT. If you code it slightly differently, then it goes into a different resource. We can check at least the answer, we can verify whether it is 32. It is mostly 32. Let us open synthesize design. Am I running the same code? Because we get 4 LUTs. Wait, just hold on. I did not make the memory 8 bits deep. That was the problem. So basically, I'm going for the next level in this code where it is quite well locations deep, 8 bits wide. Here I'm just trying to demonstrate what is distributed RAM. That's all, right? I'm running this code to demonstrate that what is this distributed RAM. Your memory is going to be spread out on your FPGA fabric onto various slices, and lot of routing resources are being utilized. Why? Just because you made this decision to code it in such a way where you made your read operation asynchronous. So now you will see that lot of LUTs are being utilized and they're spread out. The next exercise will be to make this a synchronous activity, making this read a synchronous activity wherein I say else do the statement. Then you see it is not going to get into LUTs. Rather, it is going to go get into a very tightly packed memory structure called a block RAM, BRAM, which is in fact 32 KB deep. So a lot of routing resources are not being utilized. So hence it is recommended to use block RAM when you don't want to use a lot of routing resources, right? For bigger memories, please code it in such a way that you want it to go into a block RAM. So at the synthesis stage itself, let us open synthesize design. With a schematic. See, these are all your LUTs. Let us report utilization. See, so many LUTs got used, and they are your LUT which are used as a distributed RAM. 64 LUTs as distributed RAMs are being used to realize this. And this realization, which looks not so difficult to implement, it gets spread out a lot. So there's a whole problem to it, right? From routing resources point of view. Let's see that. See, all these are your resources which are spread out. Now, this is just 512 locations into cross 8. If it's a 32 KB memory that you are planning to realize, then it will get spread out even too much, right? So in that case, we prefer to go the block RAM way. So now is a point wherein I go out of my slice M. I'm not in my CLB. CLB structure is talking about slice L, slice M. Now I implement memory slightly in a different way. It goes into a totally different FPGA resource called block RAM. Let's look at that realization once. See here, I am actually coding a 4K RAM, which is 4 bits, 4 bits wide. Let's look at the code once and appreciate the difference. So I've declared a RAM structure which is 4096 locations deep, but I made the read a synchronous operation here, right? The same thing I put it out, my amount of resources utilized would have blown up. Now it will go compactly sit in a structure called a block RAM. The real difference to be understood is this. I would have written assign D out is equal to RAM of ATDR, then distributed. They'll get distributed into my FPGA fabric. The memory gets distributed on my FPGA fabric. Now, because I coded it this way, it is going to go compactly sit into what is called a block RAM. Synthesis is done. It is utilizing block RAM, not the LUTs anymore. The slice logic, nothing is being utilized. Block RAM 0.5 is being utilized. 0.5 meaning it has 36K. 36K is one entire block RAM. 36 KB is one entire block RAM. Half of that is 18K. So 4K is fit into 0.5 of a BRAM. That's what it is telling. Now after routing, you will see how many less resources are being utilized. I'm going to select the DRAM structure. You see that there is only one block being used. What is that block? It's a DRAM. Type block memory. You see that the structure itself looks different, right? The block memory that is being utilized. If you coded it in a slightly different way, you would have seen the realization would go out of proportion. Okay, so with this you understand that there is a CLB and there is a block RAM. So in CLB there is slice L, there is slice M, and as of now block RAM, what we've understood is it has 36 KB depth. It's a memory capacity of 36 KB. It can also be utilized as 0.5 block RAM. What are the other learnings from here? If you want to implement a memory which is sufficiently large, try to put it in block RAM. Don't try to put it in distributed RAM. But if you want to implement memory which is very small, then it is preferred to use slice M LUTs. Okay, with this, we'll also see one more situation in which we use a slice M LUT is for shift registers. Shift registers are basically flip-flops, right? So you would think at the beginning, you would think that shift register, let us say I want to come up with a 32-bit shift register. 32-bit shift register is nothing but back-to-back connection of 32D flip-flops. So we would think what resource is being utilized? What resource is being utilized in the FPGA? We would think that flip-flops are being utilized either in slice L or slice M. The flip-flop resources will get utilized, but the actual resource which is getting utilized is LUTs for shift register implementation. This is what we are going to observe. I'm running a code for a 32-bit shift register. So we'll not get into the coding. Just know that we want to implement a 32-bit shift register, and it is where it is going to get implemented, what resource it is going to use. So you should know that it is going to be using the LUTs in SliceM. Okay, this is our last tool related explanation demo for before lunch. After this, before lunch, I'll just quickly go over the slides to consolidate our findings on SliceM and BlockRAM. So at synthesis, we can actually find out what are the resources being used for a 32-bit shift register. Only one LUT is being used for a 32-bit shift register, and it is used two flip-flops, two slice registers, which means flip-flops. But the idea is to know that it is using LUTs. Let me look at the schematic. So in fact, this is my LUT. So we'll appreciate that on the implemented view. New implementation is almost underway. In fact, this is a slice M LUT that is being used to implement shift register. So we'll just quickly revise this on the slides. Hope my slide is visible.
Yes, sir.
Okay, slice M used as distributed RAM memory. Slice M can also be used for memory. We saw that the code that we wrote had a synchronous write, but an asynchronous read. So there are various configurations. We have only taken a look at single port, that's why I highlighted it in red. So if I want to realize a single LUT, this is the realization we have done: 64 locations deep, 1 bit wide. But even if you were to code as 32 locations deep and 2 bit wide, it would come into one LUT itself. So cascadable up to 256 cross 1 RAM. That is one slice M realizations, right? We have seen this. Slice M used as a 32-bit shift register. This is what we have seen. We have coded for a 32-bit shift register and one LUT is being used. Suppose you want to use any shift register well within 32 bits. Let us say a 20-bit shift register. Even then one LUT can be used. But you will tap in the corresponding line, the 20th line, through a mux to take to the output. By default, it is 32-bit shift register, but if you are using it as a 20-bit shift register, then the corresponding line of the 20th flop internally is going to be tapped out through the mux like this. So mechanism for using slice resources, this is important. There are three primary mechanisms for using FPGA resources. One is inference, what we are seeing from the morning sessions, right? We describe the behavior of a desired circuit using RTL, Verilog code. The synthesis tool will analyze the described behavior and use the required FPGA resources to implement the equivalent circuit. This is what we have seen so far. This is called inference. The other way, and the more easier way to do system level designs, is to use what is called the IP integrator flow of your Vivado, wherein you open something called IP canvas, drop in IP from IP catalog, customize it, connect it, and then run the flow. Okay, this we will be taking a look after lunch. Okay, and there is another approach called instantiation using language template options. Basically, there are some resources on my FPGA device. Whatever code that I'm going to write, whatever RTL I'm going to write, it is impossible for me to realize that resource. But there is a feature somewhere within my Vivado tool called the language template option. I can go to this, and there are a whole bunch of buffers like clocking related buffers like buffgc and so on, which writing any code directly will not infer it, but you can use a language template and instantiate it into your code, and then that particular resource can be realized. So I'm open for questions now. So after lunch, we'll be looking at a design that builds upon the IP integrator, and we will also be looking at ILA core, debug core. So that it will be lab based after lunch. So any questions to this point regarding the architecture, first level understanding of 7 series architecture? So if there are no questions, we can take a break of 1 hour and we can resume by 2 o'clock. Okay, let's take a break.
అవును இந்த రెండు
Hope I'm audible. Good afternoon and welcome back. Yeah, we'll start the session now. So, in the first half of the session today, we have explored Vivado tool. The first cut look at Vivado tool. We have seen Verilog file entry, behavioral simulation on top of that, design elaboration. After that, synthesis. After synthesis, we can what are the different things we can do after synthesis? We can do post synthesis functional as well as timing simulation. Likewise, after implementation also we can run simulation, post implementation timing as well as functional simulations. And then with the help of a simple two input AND gate, we have taken it all the way through bitstream. We have explored the Vivado tool flow to the best possible extent. We have downloaded the bitstream and configured the device to work as a two input AND gate. We have understood how pin constraining was done, right? After taking a look at Vivado flow, then we stepped into understanding more about 7 series architecture, and we wrote simple code snippets onto the tool and understood what are the resources that are going to be realized. So far, we know there is a configurable logic block which comprises of slice L, two slice Ls, or another category of CLB which has a slice L and slice M. As far as slice L goes, there are LUTs, 4 LUTs, which are 6 inputs wide. There are two F7 muxes, two F7 muxes, and one F8 mux. And there is a carry block, carry chain block, and there are 8 flip flops, right? Coming to slice M, we had the LUTs which supported memory realization as well as shift register realization. So with this background, we'll proceed exploring the tool a little more now, and we look at what is called the IP integrator flow. So in the morning session, we were writing Verilog codes, and from there we were getting into the tool flow. Now we will start with the IP integrator based flow and appreciate that this is much faster and much easier than the Verilog or VSTL RTL related flow. But both the things are necessary. Okay, in different situations you have to go for either of them. So I'm creating a folder, naming it clock 1 hertz. My intent here is to come up with a clock of 1 hertz. Why is it so important? We have looked at combo logic in the morning, wherein we apply some dip switches on off, something happens on LED, but that is addressing only combinational circuits. But when we talk about sequential circuits, we need to have a clock in our circuit, right? And if we have clocks which are running at 100 megahertz straight away, we may not be able to appreciate, like for example, let's say we want to come up with a counter design, and counter is counting up at 100 megahertz. My LEDs cannot, the flashing of LEDs at 100 megahertz is not so much evident to my eyes, right? So the LEDs will not, they may look dim, or you cannot appreciate the count happening. So for that purpose, I'm coming up with a design for generating 1 hertz clock. Okay, we'll get started. I'll start a new Vivado. And I test that an LED blinks at 1 second on and off. So that's the goal of this small project. So once you have this clock 1 hertz, what I plan to do is build an IP around it. Like as of now, in my IP repository, there is no IP that generates a clock at 1 hertz straight away. But I can use pre-existent IPs to come up with this design. So let me say clock 1 hertz. select pink Z2. Now I'm not straight away going to add a design source, right? So I'll go for create a block design. So what opens up over here, this blank space, this is called an IP canvas, because just by pressing this add IP button, you can add various IPs, you can customize it, you can connect them and come up with different digital circuits. I'm going to use an IP which is already sitting in this IP repository called as the clocking wizard. These IPs are highly customizable. You can play with the number of inputs you want. You can double click on it and you can change the functionality of it. As of now, what I want this to do is take in a clock frequency and then give out 10 megahertz. That's my intent. And then I've already written a code which is going to step down 10 megahertz to 1 hertz. So that as a Verilog code, I already have it and I'm going to input it onto this IP based design. So first let us customize this. So I'm going to remove reset and locked. I'm not going to use it. So if you observe, it's saying board level interface. So when I select the board level interface as this clock, already the constraining of this is going to happen to the respective pin which is connected to the clock on the board. So hence I am not required to do the pin constraining either via the GUI from after synthesis or implementation or design elaboration. I don't have to do the IO pin planning as we did in morning for this particular pin, because the board knows which pin is connected to the clock, system clock. If you wanted to do it as custom, then you could do this. Then you can do the manual constraining. What I want is the board level constraining, so I select sysclock. Then I'm going to knock off these reset and locked ports because I'm not going to use them in the current design. So they are available in the tab output clocks. So I'm going to remove this. So I have a clock in and clock out. Let's observe what's the value of this clock frequency, what's the value of this clock frequency. The input clock, you can leave all the default selections. At the board level clock is at 125 megahertz. It's a single-ended clock capable pin. So if you observe here, because I have made this clock, this is done at the board level and I am not able to change anything over here. But if I wanted to do it manually, please observe, if I customize it, then I can change the frequency. I can change it to another source. Okay. But now I am going to prefer to do it at the board level. So I select this clock. As I mentioned, 125 megahertz default output clock is something that I can customize. So I have up to 7 different clocks that I can generate from this clocking wizard. I am interested in generating only one output clock. So I am going to select that as 10 megahertz. Just hold on. So you see 125 megahertz clock and 10 megahertz clock. But my design is to come up with a 1 hertz clock. So you could have asked me this question, why am I doing all of this? Why is it that I am giving 125 megahertz clock and then getting 10 megahertz, and from 10 megahertz I am stepping it down to 1 hertz? That's because there is a minimum limit to this frequency. I cannot get it down below some 4.5 megahertz. So there's a range of frequencies. Okay, so I cannot generate 1 hertz straight away out of this block. Hence I'm I've written a Verilog code which I'll be adding to this shortly. So I'll go to design sources, and now I'm going to enter create a 10 megahertz down to 1 hertz clock. So this design is extremely useful for observing anything on LEDs when clock is concerned. As of now, this is blank. I'll need to take it from a pre-existent code. So we'll not get into how this code is making 10 megahertz as 1 hertz. So that's already done. So take it at the block level itself. So this is also good learning as far as the tool goes, right? You can also add your Verilog codes or VHDL codes onto your block design. So this is my diagram. This is my IP canvas onto which this is my IP that came off the IP repository which I've customized. Now this piece of code is my user code, and I want it to appear over on the IP canvas. All I need to do is right click on this and say add module to block design. So now I'm going to connect this, and reset I'm going to give to a dip switch, and clock 1 hertz I'm going to be giving it to a LED pin. So I make this external. I'm going to call this reset, and I'm going to be calling that clock 1 hertz. As far as this goes, this is done at the board level. So never do make external. If you observe, it became clock in 10 when I made external. When I do that, I'm attempting to still do the pin constraining manually. Rather do the connection automation, and it will get connected to the board interface, the board part interface, which is sys clock, which is what we desire. So sys clock. So design is completed, but our Vivado tool flow will always expect a Verilog file or a VHDL file as a starting point. But we have got a block design here, and this is .bd file. You can't simply hit synthesis. For example, with just a block design file, I can't hit synthesis or implementation and miraculously things should start working. That won't happen. See, there's a warning, some kind of a warning, but it started off because this was the top level file. It has taken this, it has taken the Verilog file, but that's not our intent, right? If I just had a block design, .bd would have never gotten into my Vivado tool flow. So let's cancel the synthesis because it is running on top of 10 megahertz down to 1 hertz, that particular Verilog code. Okay, now there's an essential process of what is called wrapping up this block design as a HTL wrapper. When I do this, it gets into a Verilog kind of a template. And automatically this has to become the top level design. So next time on, when I run synthesis or elaboration, it has to pick up this. Still it's updating. See, once it's updated, it's taken the wrapper as the top level design. Now let me run it up to elaboration. And I'll do the constraining after I do elaboration. Constraining of reset and clock 1 hertz. I still prefer to go with the GUI approach for pin constraining. In the meanwhile, let's look at the XTC file. So I want LED, which is R14, which will be connected to my 1 Hertz, and I want a switch which is M20. So let's see what design runs are happening. So each of these blocks have to be individually processed, right? So there are something called out of context runs. Let's expand. So as of now, the block that is currently running is clock 1 Hertz, and output products relating to that are being generated, and now on this clock divider. So once this is done, elaboration will be completed, and we'll open the elaborated design and we'll do the IO planning from there. So my plan is this: after I test the working of this, that indeed it is a 1 Hertz generator, then I plan to make this an IP of my own, and then I will add it to this repository. Henceforth, I want to do a add IP and to be able to get this IP. Every time I'm not going to build this IP from scratch. And this I should be in a situation wherein if I have colleagues or other students in a lab, I put this in a drive and they can pick this IP and use it. So this is just a concept level demonstration. You could come up with a more complex implementation and package it as an IP and your other colleagues using it. I think elaboration is complete. Open elaborated design. It's already open, and IO planning. You observe clock. We have not done the planning, right? We have not given this package pin. It automatically got assigned to the board part pin, which is this clock, which is H16. But reset, we have not done. So that will stay something as a user level entry. So you make the setting for reset as far as the IO standard goes, LV 33, and for this scalar port as well, which is your clock 1 Hertz, that also is LV 33. So which is our dip switch? Let's look back. Our dip switch is M20. So reset M20, and LED is R14. Okay, this completes my pin planning after elaboration, but I have got to save this onto my pin constraint file. So let's go back and check whether that's done. I close elaborated design, and under constraints I check whether pin file has been XTC file has been updated. Only two pins, reset pin and clock 1 Hertz, the IO standard, and the pin assignment. This is complete. So I run it all the way up to bitstream. Let's do it in one go. Let's generate bitstream, and then we'll test it on the board. In the meanwhile, as it runs, I want to want you to think on some important point. I'm going to turn on the camera on the board. So as of now, if you observe the board, there are only two dip switches that are available to me, right? If you are looking at other boards like Boolean board, I think Boolean board has about 16 dip switches. A Z board has about 8 dip switches. ZC104 board has about 4 dip switches. But Pink Z2 is the board that you will be working with. This has only 2 dip switches. See, in morning I could only demonstrate to you 2 input AND gate. But if I want to design something which is based on more number of inputs and through dip switches I want to observe this, it's not possible, right? In Pink Z2 board because there are only 2 dip switches. So when the number of inputs, there could be situations in which you would be having two vectors into your design, which is A and B. A could be 128 bits wide and B could be 128 bits wide, and the output of your design Y could be again 128 bits wide. In that case, how would you see? You have only 2 dip switches and you have 4 LEDs on your board. So this would not be possible, right? On the board to observe. So in that situation, we have a solution. So we will shortly discuss that after this demonstration. So there is a concept called VIO, Virtual Input Output, wherein into your FPGA design on the device, you can put something called a VIO, which is going to occupy your hardware resources, and you can actually emulate the behavior of dip switches and LEDs. You can have up to more in number, but I'm giving an example. At least easily 128 dip switches and 128 LEDs. That's easily possible. I'm giving it on the lesser side of the number. Okay, this is done. We'll open Hardware Manager. We'll turn on the board. I hope the view on the board is on. Okay, so far we have not actually downloaded the bitstream and configured this device, right? So nothing is working. So we open Hardware Manager. Now I open Target. I auto connect. And I program device. We're able to observe this LED being slow, right? It's not like too fast and too. It's not running off 100 megahertz. It's not running at 10 megahertz. 10 megahertz also I could not be able to observe. Okay, I stepped it down from 10 megahertz to 1 hertz. So I am sure that you have understood that this is working as a clock 1 hertz. What I need to do next is I need to package this as an IP because I don't want to keep building this design every time. Okay, let's close Hardware Manager. So this is our design. I don't want to build this design each and every time. So what I'm going to do now is I'm going to package it. So very easy. You just say tools, create and package new IP. So you say package your current project, and under desktop, under demo, IP repo is where your clock 1 hertz is going to be packaged as an IP. If it's under demo, it's under IP repo. I say next. and this is a place wherein I can give a different name to my IP. I can change the name. Can change the name. I would just say package IP. So finished packaging successfully. Now let's see whether in fact in my IP catalog it is available or not. So if I search for user, this design one wrapper became available. So it would have been preferred to call this by a good name, saying like it is a clock 1 hertz wrapper or something. It's a very generic name. As of now, it's okay. Okay, it seems to be available in my IP catalog or even in my diagram. Let's see, block diagram. If I say user, I'm able to drop this and use it. Okay, let's close the project. Okay, and so what I'm trying to do in the next project is I'm trying to build a counter which is going to count up at 1 hertz. So you are going to see up count on the board happening at 1 hertz. So we are going to use this IP that we just developed. So I say counter, which is counting up at 1 hertz. So counter running at 1 hertz. Again, ping Z2 is my board. Now the idea is this: I am going to straight away do this on block design. I'm not writing a Verilog code for a counter and all that. Okay, I have a binary counter. I'm going to use that. Okay, binary counter, but I will use only 4 bits because I have 4 LEDs on this board. So I'm going to only use 4. I'm going to customize this to 4. So it is asking run connection automation on this clock. So it will give connected to clocking wizard, the default clocking wizard, which is outputting, which is giving an output of 100 megahertz. But if I give 100 megahertz, this count is going to be extremely fast. I cannot observe it on the PingZ2 board, right? So that is why we have come up with this IP, which is to be added before this, which is generating 1 hertz clock. Can I do that now? Like last time, I have there's nothing, there's no user. The moment I've closed that project, the earlier project of IP, it's no longer in the project, right? So there's a process to be followed to get it from the IP repository. So I need to go to settings, need to go to IP, and I need to select the path. Remember, it was on desktop demo under IP repo. So I select this folder and I say select. See, one IP that is there in this got added. So I say apply and I say okay. Now you search for your user IP. So you got your user IP. So sys clock will be connected to the board level. It is automating it into another clocking wizard, which is not required. So let me give it as external. Okay, we'll have some pin constraining to do on this. So clock 1 Hertz is given to the clock of this counter, and this I'm going to make external. I'm going to rename this signals. Let's call this reset. Call it sys clock, and let's call it LED. So or the count, right? Which I'm going to connect to LEDs. So this is basically an up counter. Now in my block design, it's just a block design. There is no other file. Now if I try to synthesize, you see what happens, because there is no other top level file. See, it is asking what is the top module name. So hence I'm required to convert this to a STL wrapper. So it's updated. This is the top level. I'll open elaborated design and then do the pin constraining. What do I have to constrain? This dip switch, I'll need to check now. Okay, I need to check whether automatic constraining has happened, because internally this was given the board part. I'm expecting it to be connected to the board pin for clock, but if it is not, we will connect it manually. We'll connect it. I need a dip switch. I need 4 LEDs. Still, I am very much in the limits of the board as far as the dip switch and the LEDs go. I have only 4 LEDs. But what if I wanted a count which is 5-bit wide, or if I wanted a 20-bit wide counter? I would not be able to see because I don't have so many LEDs on the board, right? So all this is going to have a solution in something called VIO, virtual input output, wherein I can emulate these dip switches and LEDs because they're not available on the board through something called VIO, virtual input output. So I first plan to constrain the LEDs. So this will be our most significant bit pin. M14, count 3 will be mapped to this, and count 0 will be mapped to this. Let's see the design run. What is the status? One of the IPs is completed, the other IP is going on. This IP is in progress. You may often get an option of running 2 cores or 8 cores. So maybe by default I did not give that option. It appears to be that it's running one at a time. But if I had selected 2 cores at a time, both would have parallelly processed. Now it is sequentially happening, and let's say our block design have up to 8 different IPs. If I select 8 cores, all of them parallelly start the processing. So you would get the result faster. Okay, I think this is relating to the source or the clock pin. Let's see whether it is constrained or not. So yes, this clock did get constrained at 16. So everything by default I set to LV CMOS 33. Let's constrain the LEDs. Most significant bit M14, then N16. M14, N16. M14, N16, P14 and R14. M14, N16, M14, N16, P14, R18. P14, R18. Now coming to the reset dip switch. Automated to whatever was earlier connected, M20. Because it was part of the IP, right? In the IP, we have already made that connection, so it is connected to M20. So let's save the constraints. See, I'm just doing a control S. When I do a control S, save constraint is happening. Or a more graceful way of doing it is go to constraint and save. I'm going to save it in pins. So I have my design wrapper as well as I do have my constraint. Right. Let's generate bit stream. There's some more time. We are early on in the Vivado tool flow. Few more minutes to go. The synthesis is underway. We have started implementation. So sometime back, I was telling you that there is something called language templates, right? So there are often situations in which we need to access resources on my FPGA, which cannot be inferred by my RTL code. But language templates is the answer in that situation. For example, if I want buffg, buffg is actually a clocking resource. So this is available here. This template is available here, buffg. So you just got to pick this template and paste it in your code, instantiate it into your code, specify the input and output to this. And then your tool knows to pick up this resource which is available on your FPGA device. So there are many other buffers and many other resources that are like this. There seems to be some mostly issue with the pin constraining. Okay, let's open implemented design. Maybe I forgot to give this as LVC MOS 33. and reset is W6. Let's check that. Dip switch. What is W6? This, I think by default it has changed to something else. Okay, this was not the constraint that I gave, right? So let's give it as M20. It's just going to launch the implementation. It's not going to run the entire flow. I'll close the previously implemented design. So bitstream generation is complete. Board is connected and powered on. We'll open the hardware manager. Let's program device. I have this bit file and I program it. I think you're able to observe it, right? The count has started counting up at 1 second. So once it becomes all ones, then it becomes 0. 1, 2, 3, 4, 5, 6, and so on. Okay, but this is the starting step. For most of us, we want to observe something on the board. And we want to observe something on the board, so we need to generate clock at 1 hertz and clock our loads at 1 hertz. But eventually our designs won't run at 1 hertz. It will run, definitely it will run at 100 megahertz or 10 megahertz, right, at a high frequency. In that case, we are not in a situation to observe it on the board, are we? If it is running at 100 megahertz, we are not able to observe it. That is one scenario in which we have hit a roadblock, right? It appears at this point. And the other point is, on this board that you'll be using extensively in the next few days, I have only 2 dip switches and 4 LEDs. But what if I want to come up with something with which I want to check some functionality, which is having an input of, let's say, 500 inputs and let's say 1,000 outputs? It wouldn't be possible, right? In that case, I go for something called VIOs. So just to motivate that, I'm going to give, let us say, four four input by 4 input multiplier. We'll have the product as 8 bits, right? So we'll try to build that design. Definitely it's not possible to test on the board because I have only 2 dip switches. So in that case, I will show how I can use something called a virtual input output module, which is available as an IP in my repository. to be able to apply such inputs. So let's start the next project. So I'm building a multiplier. I'm building a multiplier which has 4 inputs. A and B are 4-bit wide, and output is, the product is 8 bits wide, right? I'm not going to give all these details for the name. Let's say multiplier. I'm not going to come up with a code level, Verilog code level description for this. Rather, I'm going to do all of this at the block design level itself. Let's create block design. Let me call it multiplier. I'll just search for a multiplier block. I can customize A, B bit, and this is my product. But it's not a combinational circuit, it's based on a clock, right? So I will need the clocking wizard over here, right? And let us say that it is clocked at 100 megahertz only. I'm going to customize it. 8, 8, and 4, 4 are my inputs. A is 4 bits, B is 4 bits, product is 8 bits. And I leave the multiplication as unsigned. A is unsigned, B is also unsigned, and the width of A and B are 4. A and B are 4 bits wide. Here it is possible to realize using LUTs, or when you say mult, there is one more resource which I have not discussed, which is going to map into what is called a DSP block, DSP slice. You have DSP 48. See, this is what it says. Select this, use LUTs will build multiplier using slice logic only. Use mults will make use of DSP 48 slice resources. So let's leave it at use mults. Let's see what is our output. Output is 8 bits wide. So when I run connection automation, it's only asking me to connect it to the clocking wizard. I'll knock off reset and locked from this. This is at custom. I'll keep it at sysclock, so I can save time. Instead of, I remember it's at 16 pin, but I want it to be automatically done. So I select sysclock. Input frequency is 125 megahertz. Output frequency is 100 megahertz. Input is 125 megahertz. Output is 100 megahertz. If you regenerate layout, it looks more clean. Okay, then I say run connection automation. This is going to get connected to sysclock. Do not make external. Now I'm going to say that, okay, I want to give 4 dip switches, and 8 LEDs. It would have been possible if you are using some other board which supports 8 dip switches and 8 LEDs. Z board definitely has 8 dip switches, 8 LEDs. You could have done that. But right now there are only 2 dip switches and 4 LEDs. So I need to use what is called as VIO. So let's include that. So the output probes are going to be applied as input. Whatever value that I put on dip switches, this probe out, though it is called probe out, eventually I'll be using internal dip switches to send data through these lines. So I need two probes, two output probes, which are 4-bit wide. And the output that is generated by the multiplier is applied as input to this probe in. And that has to be 8 bits wide. So input probe count is 1, but output probe count is 2. What is the width of this? Width of this is 8 bits because I'm going to give that output and apply it as input to the through the input probe. Both these probes are going to have the width of 4. So this is asking for a connection automation. What it's going to do is it's going to connect this clock to 100 megahertz. VI also is going to run at 100 megahertz. See, it's saying clock source, clocking wizard, clock out one, which is 100 megahertz. It is giving whole lot of other options. We'll just select 100 megahertz, whatever default it has pointed out. Now I apply this as input. So I regenerate layout and I validate design. So I'm not required to do any pin constraining on this. Just that sys clock is the only input to this, which is anyway coming at the board level. So let's wrap this up. As I told you, no pin constraining. So we go all the way through bit stream generation. There are 3 blocks now. You see that all the 3 are parallelly processing. You've got to understand that VIO is being implemented on my FPGA. This is never part of the design. So after you test this, it's required to probably remove it. If this is only a design in a very complex design, just for testing purpose, if you are using this VIO, eventually you got to remove this. It is situational based. Okay. So synthesis is started. Now implementation has started. So in the meanwhile, we can open synthesize design and see what are the resources that my VIO is occupying. Let's report utilization. So debug hub also is auto instantiated. So this is for information to go from the board to your PC, right? On your PC, some waveforms are going to come now. If you are using your ILA or VIO, which are called debug cores. Right now in our design, we just have a VIO. Whether you are using a VIO, which is like to emulate the usage of dip switches and LEDs, or you're using a ILA, which I'll shortly explain. It's almost like planting in a CRO onto your design to probe some particular tracks on your design or pins. So as of now, it shows 0, but after implementation, you will see that debug hub is also utilizing some resources. You see, VIO has occupied 35 LUTs, 311 slice registers. Clocking wizard has used BuffG control 2, and it has used what is called MMCM. This is a resource available on my FPGA. Okay, let's wait for the implementation to complete. Once implementation is done, I'll actually open the device view and show you how many resources VIO is occupying. Like for example, in this design versus this and this clocking wizard and your multiplier, which is actual design, this is not your design. This is something that you're putting in there so that you can test your design. This is occupying massive resources. This is what we'll understand once implementation is completed. Almost done. Last few minutes or a minute more. It's gone up to bitstream. We can take a look at the implemented design. Open the device view. This is where your design got implemented in this part of your device. I'm just going to highlight VIO just so that you're able to appreciate out of this big design how much is in fact your VIO. So it says highlight leaf cells in a particular color. Let's put it as default. So much. Okay. And let us, the debug hub was auto instantiated. That also I'm going to highlight leaf cells. Almost the entire resources went in debug hub and VIO only. See, out of this entire PL FPGA side, this is your PS side, this is your PL side, FPGA side of things. Almost the entire resources are taken up by VIO and debug hub. Also, let's see the report utilization one more time. So now you will observe that debug hub also the resources utilized have been listed. Okay, let's actually open hardware manager, start the board. See now, along with the bitstream file, you have a debug probe file. Whenever you add in these debug cores, which are your VIO and ILA. As of now, we have a VIO. You have a debug profile also that needs to be sent in for programming or configuring. You can add your probes. So 0, 0, result is 0. 4 bits wide, right? FF. F into 0, 0, 0. F into F, I hope you can calculate and check. E1 is the result. F into F, E1. D2, E into F, D2. So this is how you are able to observe it. But now it's not looking like dip switches and LEDs, right? It's possible to configure it like that if you wish to. If you wish to see it that way, you will say toggle buttons. Then expand it. Now it's like dip switches, right? And this also you can make it appear like LEDs. Okay. So with this we are completed VIO. Just give you a 2 minute break, and after that I'll be looking at a ILA. Okay. Once we complete the ILA design, I'll give you a gracious break of 15 minutes, and after that we'll have another session. So I am breaking for a few minutes. Let's start by 3:20. So there is one more design that I want to go through with ILA, right? So that will take about 15 to 20 minutes. Okay, let's start the last demo for today from my side, which is on ILA. So let's suppose we have a design of a counter running of 100 megahertz and it is counting up. If we want to observe this, it's impossible to observe this on LEDs because the count is happening extremely fast at 100 megahertz, just not possible. Then you will have to use something which is very similar to a CRO in an analogy perspective, wherein you have to drop, instead of a VIO, you will be dropping in an ILA over here and you will be tapping the count lines. So that's what we are going to observe in the last demo for today from my side. So let's say a counter which is running off 100 megahertz. How do I observe this counts? Using something called ILA. So counter, I'll also put in a up down feature to it. The board is going to be pink. We create a block design. So again, I put the counter, binary counter, and let us say I want to watch all the 16 bits, 16-bit counter, and for up down. So I select up down feature of it. It's asking me for a connection automation. It's basically going to connect to a clocking wizard, which is running at 100 megahertz. I again remove the reset and locked signal because I don't plan on using them. Connected to sys clock. Output clock is 100 megahertz. I'm removing reset and locked. I run connection automation to connect it to sys clock, which is my board part. Just to show one more IP called a slice, I'm going to basically I'm having 4 LEDs, right? Let me show what happens to the 4 LEDs when the 4 least significant bits of this 15 down to 0 are going to go to those LEDs, 4 LEDs. So I'm going to use something called a slice. Slice basically is planning to take on all the 16 bits as inputs, but then only going to take the least significant 3 down to 0 bits. The 4 bits, it's going to take all this and it's going to route out only the least significant 4 bits onto the LEDs. So let me make this external. This is also to be connected to a dip switch, right? So that I can make the counter count up or down. Let me call this up. When up is 1, the counter is counting up. When up is 0, counting downwards. let me call that as LED. So these LEDs are going to flash on and off at 100 megahertz, because this is clocked at 100 megahertz, right? This counter is counting up at 100 megahertz, and it is 16 bits wide. I don't have 16 LEDs on my board in the first place. So I'm planning to use an ILA to demonstrate how we can observe these counts. So this is an integrated logic analyzer. Select it to native because I am going, and I would need this only when I'm in an embedded system domain wherein I'm talking with the processor. Select this as native. Is going to represent and this is going to be connected to 16 bits. This data and trigger will be understood when I give a demo in a while. When I have downloaded the bit stream on the board and I'm demonstrating ILA, you will understand what trigger is. So by default, I'm setting both of them to data and trigger. This connection automation is going to take this clock and connect it to clock out one, which is the clocking wizard.
The screen is not visible.
Did it stop sharing just now?
Yes, sir. From a few minutes back only.
Okay. I think there was a message that came in and suddenly, okay, thank you. It's visible now?
Yes, sir, it's visible.
All right. So I just have dropped in my ILA and I have given it to the clocking wizard output. This I'm tapping my 16-bit count output, and this I'm tapping my up down 9. So that's all my design is about. So I regenerate layout. The output of this I'm planning to connect to LED. Okay, we'll wrap it up. We'll create the HTL wrapper around this, and once we take it into bitstream, we are going to explore this ILA. How this ILA is going to help us monitor this count, which is counting up really fast. Let's wrap our block design. So this sys clock is constrained at the board level. Up and LED is something that we have to constrain. So let me pick the previous Okay, I may have to still do the constraining. Okay, let's let's run it to elaboration. Just to be ready about the pins. So this time I'm going to be using M20 for my up, and the 4 LEDs will be eventually constrained. Let's look at the status of this design run. In the meanwhile, let's do it one more way. Okay, we will do it not through GUI, but rather we'll do it once, but doesn't allow us to add constraint at this step because I'm already running the elaboration. Nevertheless, we'll do it using GUI itself because elaboration is going to complete. Till that point, it does not allow me to add any sources. So one final ILA IP is generating its output products. Okay, elaboration is complete. You see that sys clock was constrained automatically. Up, you will constrain the IO standard as LV-CMOS 33. For the LEDs also LV-CMOS 33. So up button is to be connected to M20. What about the 4 LEDs? The most significant bit is on top. Let's search for LED. So it's going to be M14, N16, M14, N16, M14 and 16, P14, R14, P14 and R14. I'll ensure one more time that all these have set to LVCMOS 33. All my LEDs are set to LVCMOS 33. The pin constraining is done. Up also has been constrained to M20 LVCMOS 33. Clock was by default done. So let me save the constraint. And we'll run it up to bitstream. Meanwhile, let me check whether I can still look at this. You see that it is talking about a sample depth here. This is something important to make a note of. The sample depth is talking about the PRAM. Okay, I talked about PRAM memory resource, right? It's just a RAM. It is going to be storing your count values. So what's happening? Count is continuously going from all zeros to 15 highs, right? 15 ones. So 0, 0, 0, 0 to FFFF. So all these values in a depth of 1024 will be continuously being uploaded. And when you hit a trigger called up, what is in VRAM that is going to be displayed. You'll understand this when I actually show the demo once I open the hardware manager. So it is possible to change the depth. If you want to see more number of sample values, you can change the depth. So the more the depth, more more is the VRAM resource that is going to be utilized. Let us leave it at 1024, not worry about it too much. So synthesis is completed. So we'll open synthesize design and check how many resources my ILA is taking. See that ILA is taking a VRAM resource also. Because I have selected it as 1024 location, it is taking 0.5, which is half of my VRAM. Let's wait till it generates the bit stream. In the meanwhile, let's open synthesized design. So let's open schematic. Let me get deeper into the design. See, these are marked debug. These nets are marked for debug, right? The other lines which are not marked, if you wish to debug them, you can still mark for debug. Okay, this aspect you can explore. we have included ILA in the block design, because of which these mark for debug has happened. But deeper in the design, there are some lines which are not marked for debug. If you wish to, you will right click on the line and you will say mark debug. And after that, you will say setup debug and you will save the constraints to the constraint file and then run the Vivado flow. So what is the difference between the two aspects? What I've done here in this experiment, in this lab, is I've dropped in a ILA and I'm tapping the lines. But after synthesis, some nets which are deep in the design may not be tappable at the block design level. So the tool offers me an opportunity to tap lines deeper in the design by opening synthesized database, right clicking on a particular line and saying mark for debug, and then you set up debug and save the constraint to the constraint file. What is getting saved is your debug constraint information. So let's open hardware manager. This looks like a previous design, right? Let me just turn off the board and turn it on one more time. Open hardware manager, open target. Now I get a bitstream file and debug probe file. In this, there is information relating to ILA. See, now I have my ILA window open here. If you observe on the board, these LEDs, the intensity is different, and you see sometimes infrequent flickering of these, because at 100 megahertz they are running, right? You really can't make out any change. That's why we put in that ILA in over there. So I'll add the upline which I'll be using as a trigger. So if you observe here, my dip switch or the up switch, I hope you're able to observe this, is 0. On the 0 side, and the program is already running, right? That's why count is happening, but really I'm not able to see anything. It has already started counting and it's continuously counting, not just the 4 bits, all the 16 bits internally are counting up, rather counting down, because they are at this is at 0. So now I'm going to make this 1, okay, up button 1, and I'm going to run trigger for this ILA core. What is the actual hardware condition? Actual hardware condition on the board, please observe on the board, is my dip switch at 0. But I am triggering on a situation whenever up is 1. So it stops and it waits for the triggering situation to happen. So the actual hardware condition that exists on the board, which I'm pointing with my finger on the dip switch, is 0. But on the tool, the trigger happens only for 1. That's why it is waiting for it. Internally in the BRAM, storage of the counts is happening, but only when the match happens. Now I'm going to make it 1. You see that around the trigger before 0 and after 0 when it is 1. So I can zoom in and I can observe that for 0 there was a down count that was happening, and after when it became 1, the up count has started. Right, this gets to the end of our session on ILA. Is there any questions for me? I'll be giving a break for some time now before my colleague will take up Questa Sim and other aspects relating to code coverage. Is there any questions for me? I'm also sharing this feedback link, so which you can fill up at the end of the session. Okay. Okay, please don't forget to complete this feedback form at the end of session today. Thank you so much, and we'll take another 15 minutes. We'll take 10 minutes break. We'll again resume by 4 o'clock.
Sir,
Yes.
sir, we have doubt in software download, sir.
Which on the Vitis side?
Yeah. Hi,
Yeah,
yes.
that will be dealt on.
Hi, Sankal Prakash here.
Yes, yes.
I'm there. What is the problem, my dear friend?
Sir, sir told 36 GB only for that software, but it taking 200 GB. Sir.
No, who said 36 GB?
Sir?
Who said it's 36 GB?
So while conducting in meeting, they told that the file consists of a 36 GB, but while we are downloading the file, it comes under 104.
Prakash, Manjunath here.
Yeah, Manjunath.
So I told the whatever VTs they have to install, it is around 30 GB I told. So maybe
Okay.
they have selecting other packages too. That's why it is getting.
Okay. Well, Manjunath, they have to
So
install
what
the
packages you
whole
want to
thing.
download for this, sir?
Okay, see, we have shared the software downloading link in the agenda also, and in the mail also it is there. You can download that software, okay? And maybe today or tomorrow I'll show you how to do the installation also, okay? And regarding licensing, Chipin team will help us. Exactly.
Okay, sir.
Okay.
Thank you.
Chipin team, anybody is there? Prince, are you there?
Yeah, sure, sure.
Okay, right. So make sure that you have the license variable set up everything with it, and then you can release that one.
Yeah,
Okay.
sure, sure.
Sure. Okay. Sorry for disturbance, Sakal. It's because it was a question regarding the installation. That's why I just came off for that.
No issues, Prakash sir. We're done with the session, and we'll resume by 4. Manjunath will be taking over from 4.
Okay, right. No problem.
Okay, I've shared the link. All of you, I've shared the link for feedback. After the entire session is done, please look back in the chat window and give feedback. Thank you.
Sir,
Yes, ma'am.
know that how to access LEDs.
Can you please speak a little louder, ma'am? Or put your question in the chat window.
Yes. Can I please know that how to add the sys clock and LEDs in the diagram area?
So you are saying we have a block design. Let's go back to the block design. I think your question is at the start of the flow. Let's open the block design. So you're saying what the question is how to add sys clock. Is your question? So your question is how to add it, how to create the pin constraint?
Yes, sir.
So what I have shown is I've demonstrated in this session only the GUI based approach. So here, for example, I'm going to delete this. Okay, sys clock. Here it is at sysclock, which is the board interface part. If I select it as custom, then I'm required to do the pin level constraining, but I'm connecting it to sysclock, right? And then I say run connection automation, select board part interface. So it got connected to sysclock. So this is automatically constrained. So I have never constrained this. But for this up counter, when I have connected this up switch, I need to connect it to dip switch. I need to connect these LEDs, this output line to 4 LEDs. I have done elaboration. After elaboration, I have opened elaborated design. And you have a GUI for IO planning. So this is the place where you can do a lot of different kind of constraining. Now, by default, IO planning is selected. You could do floor planning as well. We don't discuss that in today's session. So IO planning. So it lists all the input and output ports of your design, out of which sysclock by default, I did not do this even before. It was automatically connected to H16 because it's a board part pin, sysclock. But for these up, it is not listed as a board part. For this, I looked up an XTC file, master XTC file. You just have to Google for pink Z2 master XTC. Pink Z2 XTC. First link that opens up on GitHub is what you'll be using. So you need a dip switch information. So find SW. We have 2 dip switches. So the one of the dip switch is connected to M19 pin on your device. Other pin is the M20 pin. So you provide that information. What about LED? You have 4 LEDs. These are the pins. You refer this and then you update this table, right? The package pin you are going to update. So is the answer clear?
Yes, sir.
Okay, we are almost close to 4 o'clock. We'll just resume by 4 o'clock. Okay, I'm going to mute from my side and my colleague is going to take over in a few minutes. My colleague Manjunath is joining in. Kindly make him the presenter. I'll be logging out from this meeting.
Hello. Yeah, good afternoon, everyone. I hope I'm audible to all of you and my screen is visible. Okay, thank you. So, as a continuation of what Sankalp has mentioned regarding the Vivada flow, so we have come into the one portion of today's agenda, that is on code coverage. So, myself, Manjunath, working as a senior application engineer with Coral Technologies. So today I'll be taking you to the uh, the detailed code coverage, and then how you can, if you have a set of codes, in the like if your own designs are there, how you can check your code coverage, both in Vivado as well as the other tool which is QuistaSim. Since you are handling with the FPGA design flow, so Vivado is one of the major uh, tool provider for the designs on hardware implementations. So let us get into a stepwise to understand what code coverage is first initially, and then followed by that we will go ahead with the next level of understanding how we can implement in Vivado. That is first part, and then we can check on the uh, Vista Sim part, so which is parallelly similar to Vivado Flow, Vivado Design Suite. So we have Vista Design Suite, so where we can do perform a verification and then code coverage, all those things. But our area of constraints is on code coverage. So let us get into what code coverage is. If any point of time, if you are having any questions, please feel free to ask. So regarding this code coverage, so what basically code coverage is? So basically, whenever we write any Verilog, VSTL or C language program or any other language program for basically for your hardware understandable codes, okay, which is basically in HTLs, I can say, so which your hardware can understand in terms of a bit file or either zeros or ones in bit file. So what are the tools available for us for performing code coverages? So we have a integrated model sim, and then apart from that, Xilinx simulator we have. Apart from that, we have also have a Quista sim also. But when we talk about particular the vendor, so particular to the FPGA or any RTL design tools. So particular to those tools, so we have simulators, which will those simulators will take care of the code coveraging portion. So what are the advantages of having these multiple code coverages? So one thing is, so you can have like, so with one tool itself you can have learning capability and then understanding how code coverage will be covered. So and there will be no instrumented code is required for, especially for that. So that means at the back end we are not required to have other tools will be taking care of this code coverage. So whatever the tool we have should be taking care standalone operations. So that is the main agenda of code coverage. So whichever the tool we take, it should be having a capability of handling the entire code coverages. So what are the support? As I mentioned, so on HTL part, so we'll have VSTL, Verilog, and System Verilog, which is basically for hardware description languages. So these language supports are given for the entire code coverages. So we these code coverages will impact in about 5 to 10% of performance of your designs. So that's why we couldn't able to. There are certain cases we can achieve 100% of the code coverages, but there are margins. There are 5 to 10% of the margins where the coverages cannot be possible in certain extent. So which will can be accepted. So that is a main motto of having code coverages. So what are the metrics we will measure in terms of coverages? So one is with a branch instructions, branching instructions, how many branch instructions we have. Uh, that will cover with the branch metrics. And then next we'll have a conditional checking, any true or false conditions. So evaluation of the conditions will be taken care in the condition coverage, and then we'll have expressions. So when we have any logical expressions, that will taken care by expression coverage. And then next is statement coverage. That will gives us any statement, we will make it like an direct assign statements like data flow modeling and all. So how the coverages are done, that will be taken care by statements. Next, the logical transitions. So that will comes into a toggle. So whenever if we take any variable, so that will work on the binary aspects. So how many times the toggling is happened? Suppose if you take a clock only, how many times the rising edge is appearing, how many times the falling edge is appearing, that will be coming under the toggle coverages. And apart from that, the finally we have FSM models. If you have any FSM models, what is the initial state and the next state? Okay, all these things you can visualize using the coverage metrics of an FSM. So that will be taken care by FSM coverage metrics. So these are the major metrics that we follow for your entire code coverages. It's like there are certain semantics, okay, that we have to follow in coding aspect. So that will be taken care by the compilation aspect. So that is nothing to do with this part, but how many statements you are covering in the entire flow, whether the logics are covered, everything will be visualized using a code coverages tools. So what are the things we can explore here is there are majorly on the metrics evaluation of these coverages. We are going to view in the graphical windows, and then each metrics we also visualize using a graphics wave, where we can visualize or display the metrics of whatever the coverage metrics are there, and then how many missed coverages are there, whether we can do something with our code so that it can be covered. So that can also be possible, provided certain aspects we need to follow that. So those are the things that we have to concentrate on the code coverages. So even certain times what will happen, the code coverages I have done now, the later part I have to observe the reports and all. So we can perform that, we can saving this coverage database after the like post processing analysis we can perform. That's why like later part when the simulation is done, and then we will tabulate all the coverage metrics in a file, and then we put it as a database that can be used for the further processing or doing any analysis of the assertion based designs or verification based designs and all, so that we can keep it as a database ready. So these are the things which you need to understand. So we will see one by one the code metrics. What are the metrics we have in terms of coverage? Starting with the statements, statement coverage. So the statements, whenever we assign some values, so we have like in this example what we have taken, z is equal to 0. So we have one countable statement for statement coverage. So it will stays that so z is 0 means, so whether these statements are covered in our designs or not. So and then we take the conditional checking. So if x is equal to 1, x is equal to 0, then z is equal to 1. So now the part of the statement z is having either 0 or 1. So both the things are covered in the statement coverage. I can say with the small example we have given here, always at x or y begin z is equal to 0, initialize with z value 0, and checking the condition of x. Based on that, the statements are changed. So the statement z is having a single bit of information, scalar quantity. Either it will take zeros and 1, then I can say it's completely covered with the statement coverage aspect. That is one thing. So this is one aspect of the coverage. So next, coming to the branch coverage. So whenever we use branch instructions, so suppose we have if else statements, okay, if else or if else if statements. So we need to understand how many branch we have. Okay, suppose if I take two variable function, so that means a vector. So let us say x only, which is having a two variables, then possible combinations are 4. So we can have checking x value becomes 0, 0, 0, 1, 1, 0, and 1, 1. So that will gives you about branches. So in certain cases, like example of multiplexer only. Okay. So when we take a multiplexer 2:1 mux, okay, then or 4:1 mux, based on the select line value, your deciding factor will happen, right? So entirely like whether the values of select line are covered. Okay. So with the selection of that select line, we could able to achieve whether the inputs, how many set of inputs we are given to your mux, that will be communicated at the output portion. So in this case, we'll assume this to be yeah, 2:1 mux. In one of the example, you can say here, if x is equal to 0, then z is equal to 1, and else we have z is equal to 0. So that means x can be acting like a select line here. So we have 0 and 1 given to two inputs of your multiplexer. So this is a branch now. The x is covering 0 as well as 1 possibility in the else condition. So similarly, for if you take 4:1 mux, so we'll have 4 different combinations. So x is equal to 0, 0, else if x is equal to 0, 1, else if x is equal to 1, 0, and then else condition 1, 1. So the last value. So all the 4 combinations we can cover it with a branch coverage. There is one statements we have taken. Apart from this, we can have it the similar analysis in terms of case statements as well. So the case is also one of the branch instruction. I can say case of x, when x value becomes 1, 2, 3. Here they taken an x values and integer values for the second examples what it is shown here. So based on the values of x, so we are predicting. It is not similar to your multiplexer, but it is a conditional checking. So where we have a branching of the x values. Okay, when x value changes, what will be the output value z which will be covering. So if we have the statements like if else or case statements and all, so that will comes under branch coverages. So I hope you understood what is statement coverage and branch coverage, right? So any doubts till now? Kindly, if you have anything, just let me know. Otherwise, if it is good to go ahead, so we can go ahead. Yeah, from the audience side, anything? Yes. Okay. I'll just come to that point. So toggle point. Okay. So I hope I'm clear till this point. Okay. So next we have the expressions evaluation as one of the expression coverage. So how the expressions? So what are the expressions we have? We have expressions written, which any values on the RHS side you have written, any assignment statements you have written using gate level implementation or the data flow implementation level. So that will be affecting the left hand side of the logic. So that will be entirely an expression I can say. So with that expression, so we can evaluate the design aspect. So whether the all values of the logics are covered or not. So in terms of an expressions, so which is evaluated on the RHS side, so of the design, and that will be assigned to an output. So that expression, whether it is covering with respect to the your LUT, it's typically LUT in the sense your truth table is itself. So you can have an expression coverage whether these expressions are covered or not. Okay, and then there are certain cases where you have an unknown values also covered. So that is also be possible using an expression coverage. So that is regarding expression coverage. Moving on to the next one, conditional checking. So this here, the conditional coverage will have it's a extension of branch coverage. It will evaluate in typically in VSTL flow and all. So we have conditional coverages where we can operate in ternary operations. So and we have statements called if the statement is true, then or when command, when this value is the x value is become 0, then what will be my output. So that we can rewrite in VSTL as well. Similarly, in Verilog also we can have a ternary operator when we have the conditional checking. So inline commands also in multiple commands, if you have multiple lines of instructions, if you have, so you are going to merge into a single line of command with the ternary operation. So then we can take the logical expressions to be covered under conditional coverage. This is one of the example of line 180. That so we have taken this from some of the designs. So this is one of the instructions is mentioned in VSTL. So that will be covered under conditional coverage. Coming to a toggle coverage. So what I was mentioning, whenever the logical transition will happen. So whenever we take any variable declared as Verilog constructs, Verilog data types or VSTL data types. So we'll have, like in Verilog data types, we have wire, register, bit, enumerated type, real, that is floating point, short real, short int, so integer type, byte. So when we talk about any memory aspects, defining an array, structures, packaged unions, so time data types and your integer data types, all these things are covered within Verilog. So any variable you can declare with any of these data types. Similarly for VSTL also we'll have Boolean, bit, bit vector, standard logic and standard logic vector, and arrays and records. So all these data types are supporting for variable declaration. So what are the toggle one? So we have a standard and extended mode. So standard, the logic transition. So that is from 0 to 1 or 1 to 0. That is a standard way of observing the toggle coverage. And in extended, we have the coverages of taking from 0 to high impedance state, or 1 to high impedance states, that is your Z state, or to in the reverse way as well. So taking from 0 to Z or Z to 0 or logic 1, like that. So we can cover as a one of the metrics in the toggle coverages. So apart from that, we have FSM. So FSM is basically your finite state machine. It basically covers the states. So what will be the initial state, and when there are in the FSM also we have idle state, and if there is no operations are performed, the idle state will be executed, and then it will further go to the next level. So provided your the state value changes, so there is a transition table you are going to write. So based on the transition value, so whether it has to go from one state to the other state, so that will be decided by your FSM coverages. So that is the main construct. So what we follow in the coverages. I think the you got an insights about what are the coverages we have seen, right? Now, whatever we have learned now, the same thing we will implement. So not all the coverages which is required for your applications or understanding. So only we concentrate on statements, branches, and conditional, and then toggle. These are the four major coverages we are going to look in. So which is essentially required in any of the design. So we will always concentrate on the statements, conditional checking, and the branch statements. So toggle can be, there are few things where requires a logical transition, logic to be covered. But majorly these three things are essentially we use it. So when we talk about the coverages, so majorly with Vivado flow as well as with the Quistasim. So in the Quistasim, when we compile any of the designs, for VSTL programming, we use VCOM as one of the instructions. So, which is basically a, I can say it's a transcript or a tickle script, I can say. So that command will be used for compiling your any of the VSTL. VCOM is for your VSTL code compilation, and VLOG is for your Verilog compilation. And whenever we use VLOG with some file name plus cover, that means it will be taking care of the cover, and then with switch. So F switch is stands for your FSM coverage. Okay. Similarly, there are certain things. So what are the coverages are there in the Quista sim portion? So that I will be covering in the later part. Now, last as a first step in the code coverages. So we will go ahead with the Vivado code coverage design. So rather, I'll just tell you how you can go ahead. So let me start up with the basic Vivado. I hope till this it is fine for all of you. Okay, so there are questions. Yes, says yes. I'll be sharing you. So Prakash, is it shareable, the PPTs? So I'll just consult Prakash, and then accordingly I'll just share you. So there is nothing much in the PPT as well. So the few things I'll tell you, you can note it down. So which is required for your analysis. So that will help you in the coverages portion. So I'll tell you what command you required and in Vivado and what is required. Usually we will follow with the GUI method only, but Vivado doesn't have that GUI method of extracting the coverage part. But we have one command where you can directly take the coverage data. So I'll just quickly create one project. So I think you have come across with this. So what I'll do is just take one folder location. Just take one folder. So I'll take this path, just provide it to. Okay. So in that, so let me take some design. So I'll not specify source at this time. Think just go to pink Z2 board. So nothing to do with board and all, but essentially for creation of the project, we required. Can select anything, any board, but if you are design pertaining to specific board, then you have to select the specific board. Otherwise, you select any random board. So our interest is code coverages, which will be software based, so which is not communicating with an hardware. So entirely an RTL. So we'll create one design source. So create file. We'll just take simple counter only, counter design. Just finish. The module name counter. So I'm not specifying any IO. So I have the ready code available as of now. Let me use the code available already. So I'll just take the counter. So it's a counter. It's not copied. Now the counter. So just I have a glance about the code. What we have: counter, clock, reset, count. So we declared count as 4-bit counter. So clock reset we have always at positive edge of the clock begin. If reset is 1, then count value becomes 0. So else count value becomes incremental. So that is what my code is. Next, so as soon as you have any code error free, so it's not taking. Just save this. See, there is a syntax error here. So the tool will tell you. So whenever you have any error, so that will highlight, underline the particular line. So you can make sure that you can debug that portion. So now let me add upon simulation part. So I'll add simulation source. So basically a test bench. Just select. So counter underscore test I'll give as the module your Verilog file name. Then just finish. So I'll take the readily available test bench, what I have written. So I'll just incorporate in the test bench. Save it. Yes. So we have some error. Just error. So just some messages. Yes, we have it here. So it's initial clock. Here there is semicolon is missing. So I'll save it. Yes, so it is error free now. So you can see it. So what are the main aspect? So now I have a code. So let us glance the code what we have. So module counter test. So there is no parameters are listed since it's a test bench module. So acting like a top level module for the design. So I have declared a clock and reset as a register and then wire as a count. And I have invoked the top module with this counter. So I am followed with uh, the directions. So aligned with the ports. Okay, your variables are as aligned with the ordered list, I can say. So clock is first, reset is next, and count. Similarly, I have defined here. Then initialized clock value with 0 and reset value 0. So always hash 5 clock is equal to negation of the clock. So we made the clock to toggle at every 5 nanoseconds. Then we taken the for first 200. Initially it is like we have makes reset as 0 till 200 time zone. So the reset values become 0, and then we are changing after 200 nanoseconds. Reset value becomes 1, and then we made reset value to be 0, and then we are stopping our simulation at 250 after once after this. So almost I can say 400 or 650 times it will be running, and then stopping the simulation, and then we are winding up the simulation by finishing at 1000 nanoseconds. So this is what our code is. Now the major thing in the Vivado, so we will go to the settings here. So go to the simulation part. So please pay attention here. So just kindly make a note of these things which is required for your coverage metrics to be understand. So go to settings, project settings. So in this part, project settings, you have simulation. Go to elaboration. Go to elaboration here in the second tab. Here you find some coverage related aspects. So you can see here. So we have coverage name. We have to specify here. So let me give it as DB1. Okay, database 1 or any name you can give it. It is not mandatory. Okay. So next you can specify the directory name as well. So I'll just follow these lines. So it is not mandatory. So I'll just give crun. Okay, crun 1. So I'll give the directory, and then here it is important. Please, you need to understand this, why it is required, what type of the coverage you want to give it. So whether you wanted to give it for only statement, branch, condition and toggle condition, so then you can provide that. So you are going to have statements coverage, branch coverage, conditional coverage and toggle coverage. So if you want finite state machine coverage also, you can add F also along with that, so that will work. So as of now, I'll give it only for 4 prefixes. I'll just come to that, and then I'll just tell you what are the things you can give it. Click on apply or OK, you can just give it. So this is now we are made a setup to be ready for making my coverages to be done. Okay, so when I make that, so straightforward, what I need to do is I need to run the simulation. I'll just run the simulation. So simulations are run. You can see here entire simulations are covered. Okay, so once reset is 0, it's unknown initially it is taken. When reset is 1, then output becomes 0 in this condition. You can say I just first I'm making you to understand the logic with respect to the simulation, and you can get to know that whenever reset goes low, okay, at the every rising edge of the clock, so your sequence are changing. So it's basically a counting is happening. Okay, so we have all the possibilities, like counting is happening incremental. So if you want to design any up down counter also, you can, it is possible, you can do it, but provided you need to make sure that the coverage has to be covered for that scenarios. So now only with reset, both zeros and ones are verified, and the clock condition also it is covered. I think as per our understanding, we could able to say that my designs is covered. So this is simulation wise, right? So but we are not sure how much coverages are done with respect to the code. So we have to check that. So for that, what we are supposed to do is we have a code of line. Okay, so whenever we set these 3 things, no, so what we can observe in the console, so just we will see in the console, just I'll expand it. So what in the backend is happened. Okay, so whenever we have set those directories and runs, it will be setting a command. So now what are the things you can follow is, one is tickle based, I told you, right? So you have this entire tickle script, you put it in this tickle command, so automatically it will takes care that it will create a database 1, and then directory with crun1 name it will give, and then what are the type of coverage, so that will mention within this flower brackets. So these 3 lines of code essentially is replicating whatever we have performed in the GUI. So now next what we need to do, now we have to run the simulation. Next is, so we have a command. So this is the step what we followed, db1, crun1 and cbct we have set. Now we are going to write the coverage. So we have this command, just kindly make a note of this. Okay. So write underscore xsim underscore coverage. So that will be write your simulator coverage to directory coverage underscore database underscore directory. crun1, directory name is crun1, to the database name db1. So we have the database name as db1. So these things will be for making your coverage to be available for the user to understand. So I'll just enter this command. Okay, what has happened at the back end, I'll just show you. So my code is CDAC coverage design 1. So I'll just go to simulation. Inside the simulation, so I'll just go to my directory. So directory is what we name given crun1, right? So I'll just go there. So the code coverage with a database db1, right? We have this database available in this. So we have written this in this entire folder. Okay, database. So we have that information portrayed here. So which is not be readable, right? So now what we do is we'll run one more command. So we'll take this command and we build an HTML. So report to be printed using HTML. So I'll just, what I'll do, whatever we created the coverage information, which is saved in this xim.cc info, right? So that we are making it to available for the HTML report. Okay, for that we do export underscore xim underscore coverage and the database name. Okay, so hyphen cover underscore db underscore name with database name, and then run whatever the directory name and the directory report. So we are going to take it to C report, and then hyphen open underscore html true. If we give this, automatically it will pop-ups with the coverage report for you. So it will enforce who is the user and what is the version of the tool you are using, and what are the reports you are accessing. So from where you are accessing. So report directory is the report one, right? So I'll just go to this one. So we have behavioral simulator. So you can see here, see report one, code coverage. You can find all these files are available here. So if I'll open the dashboard, it is same as the what we exported. Automatically it is created, right? So how do I analyze now? So you can see here our statement coverage will be 100%, branch coverage score is 100%, conditional coverage because we don't have any conditional statements in our code as of now, so that is why it is 0, and toggle coverage score as well. Now how do I explore? So I'll just go one by one in files. So I'll just take my test bench. I'll just enable show statement coverage. It will show you what are the statements it is covered under. Okay, you can see initial clock equal to 0, so that is covered. One statement you return and then it is covered. Okay, so that information is available. So similarly, reset and clock. So two values it is covered. So execution count is 259. Everything it will take. So we have reset values also, stop and finish. All the things are covered in your design. So in terms of statement. So when it comes to, we have toggle coverage. So I'll just disable this so that you will get to know that. So register all bits of the clock and all bits of the reset, and then wire we have not covered. Wire is basically your output, right? So that is what it is not covered. So again, in like indirectly you can say that it is covered with this. Okay, so this is one way you can find how we can find the reports of your code coverage. Then next go to the files. Once again, if you want to check on your Verilog module, so Verilog module is covered with the statements. All statements are covered. That report you can see. Now branch coverage, whether the branch is covered or not. So if else statements, right? So all the branches are covered here. So that's why it is showing you 100% for that. So coming to toggle coverage with respect to the design. Okay, usually we will expect all our designs to be greater than 70% or 80%. You are having a good designs for your statement or branch or conditional coverage. If you have those statements. So coming to our modules, so each module, what is the report? We can find it here. How much score of that test bench or your design, how much it is having the score, that will infer here. So this is one part of the code coverage in Vivado Flow. I hope till this it is fine for all of you. Any questions? Any doubts till now? So these commands, so there are documentation. So maybe I'll just be sharing you. Just kindly make a note of this if you want it. Okay, or just I think if it is shareable, I'll just share you this document. So only these two commands are required so that you can view the functional code coverages for your designs. So only thing you need to have your database name and the directory where you are storing. Am I clear to all? The last test bench, you have given some delay between stop and finish. Is it mandatory for coverage simulation? Yes. Yes. So there are few things like manually you can, like if you skip simulation and all, what will happen? There are few part of the like code. Earlier way how we used to do is we have to stop our simulation and finish it, right? So that's why it's also be considered as one of the coverage part. So make sure that you will also incorporate in your designs those constructs, so dollar stop and dollar finish. So if you have any other display or time other or monitor type of uh, defining logic, then that is also fine enough. That also you can incorporate in your designs. So I hope Vivado you have cleared with. So shall we go ahead with the next one, Quista? Okay. So from audience side, so I required a reply, understanding whether they are done with like understood with Vivado. Shall we go ahead with the next one? Please either mention it in the chat or you can unmute and then speak. Okay, good. Thank you. So this simulations we have done. So I'll just exit the simulation and just close this Vivado. So since I have installed my Vivado design in, stop sharing. Just go to CentOS machine. Just 2 minutes of time. So So I'll just open the terminal. I'll just CSH. I'll just source the CSHRC file. Just another window. We'll just change it to the license directory. Since I have the tool installed on CentOS machine. One more. So you can have Vista to be installed on Windows as well. So you can have LM Tools Manager, so to take care of your licensing part. So here, since I used VirtualBox and installed Vista Sim on that, just check my status of the license. So license is up. I'll just open Vista tool. So as soon as you open the Vista tool, so it will come like this. So I'll just go to new project creation or directory. So I'll just close it. I'll just browse, create one new library. So what I'll do is project name, I can give it as sample design. I'll just browse the location. So what I'll do is I'll just go to this location. Just go to home, so that Manjunath. So I'll just take the CDAC directory. Okay, so I have this, and make sure that you have default library name as work. So by default it will take, so it will copy the library mapping. Usually if you not map it, okay, then manually you want to do it, then you have to make sure that you have to align your design library to work library. So initially only while creating a project, so we are defining that work library, which is copy library mapping. Already it is done. Okay, I'll just create a new file. So we'll create a one counter file, Verilog module, so which is of Verilog type. So if you have system Verilog or VSDL, you can define that top level module. Click on OK. So one more file name, I'll just create at a time, both counter underscore test and counter both. So both are in Verilog. Okay, click on OK. I'll just close this. I'll just open this and just copy the code which is available to me. So I'll just take the counter code, copy the same. So I'll just put it here. My code is ready. The next test bench code, I'll copy. Just copy the code. Just put it here. So the same code what I run there in the Vivado, so the same is available here for us to use it. Okay, and after this, what we have to do it. So we have the library, right? So we have the projects here. So we compile normally. When we compile, it will be different. So normal compilation which has happened. So this also you can compile, right? So now you can see here, if any compilations errors are come, so that will defined in transcripts. So in the transcript, so what are the things are there? So I'll just show you. It's basically whatever you do compilation, so it is based on the GUI based, right? So tickle script wise also you can do compilation. Vlog file name you can give it, so then it will run. Vlog, so counter dot v. If you give, so it will compile and then will tell if there is any errors or not in your file. Okay, so like simulation wise, like in the normal way in GUI based, you can directly right click and then compile selected, you can do it, right? So that is one thing. Now you can see after the compilation that will appear here, right? So the modules are appearing it here. Same way, so you can do it for your test bench as well. Vlog counter underscore test dot v. Okay, so there are 0 errors, 2 warnings. So that will be appearing, right? So now what is the next thing? What we can do is we can right click on compile and go to compile properties. So there is an option of coverage here. Okay, you can select, since my code is comes under the optimization level 1, so I'll just take that and enable. If you want toggle coverage, you enable this, and if you want statement coverage, branch, condition and expression, you enable this. Click on OK. So you can do it for this as well. So if you want individually you can do, or the entire projects also you can do it. So you can see here, so you can enable. So if you want FSM and other things, that also you can enable it. So provided your simulation demands those coverages. Okay, so now we have this, and then go to simulation. We have start simulation part, and then we have others here. Enable code coverage. When you enable this, okay, that will be available. So for the design, what are the things are required? You select. So we have counter module. So you just work dot counter, copy. So now we have this coverage report. So is there any coverage? No, right? So cannot see anything. I'll just run this. So I'll just run it for microseconds. So it is not compiled with coverage option. So we have not done compilation. Before that only we are getting into the simulation. So that we have not supposed to do. So once we made the settings, so we should make sure that we compile the designs. So we compile all will give. Okay. So compilation of both will happen. The tick mark you can find it. So once we make the enable code coverage, then we must have to make sure that we have to consider those. We will take it. Okay, the coverage. So the module, whatever we are taken, how much it is covered, that statement will appear here. So the problem is what? Here you can easily get to know. So we have only a Verilog module. So we doesn't have any simulation, right? So why it is not occurring, we have to find out. So we'll stop the simulation. If there is no statements are covered, okay, so you will get like this. So there are no statements are covered. So reset is there. This is not covered entirely, and else statements, branching, right? So reset 0 and 1 both are should be covered, right? So that we have to find both the ways. So I'll just stop the simulation. Okay, maybe the library is not taken the test file. Refresh it. So it is not taking. Update will give. We will change this to other directory. Okay, just let me figure it out. Why the counter underscore test is not getting reflected. We have underscore test as well. The path. File change directory. CDAC. So we have only counter module. File browse it. Have home. Library. Work. Just a minute. I'll just figure it out. Just a minute. I am rechecking once again. I'll change the directory. So I am taking different location now. So just close. Compile selected. Will not to library. Refresh. So I'll add one more file. There is nothing to build because there is no code, right? So let it the code, add it. Now test bench, add it. So we'll select this, compile properties, enable this, enable toggle, optimization one, enable, click on OK. Same, we'll check it for this. Coverage, simulate. So before that, compile selected, compile selected. Yeah, now it is available, count underscore test. So majorly count underscore test is acting like a top level module. So make sure that you add it the above and then you compile. So now we shall start simulation for count.test, others, enable code coverage, click on OK. So one error is there. So we have to identify what error is. Counter.p line number 6. Under test file, right? So test file is there. So error instantiation counter failed, design unit was not found. Okay, that is not found. So I'll just refresh. Update. Okay, so make sure that that also should be added. Add to project existing file. So just a minute, guys. I'll just check. Is there any other alternative so that not invoked?
Okay. Hi, Prakash here. Dinesh, you had asked me a question about what will be the pattern of hackathons. It's hackathon, or what is that? I couldn't understand. Can you hear my voice? Okay. Regarding hackathon, you please be in touch with Chipin team. They will explain to you. Don't worry about that things. Okay. So don't put any questions on hackathon things here in our session. Okay.
video. Okay, so already have one compiled design, so I have created it. Just share you. So now you can see in the work library, whenever we enable it, so it will come up in the library work for library. So make sure that both design and these are available. And then when you start simulation and read startles, just a minute, we have to enable coverages. So it is enabled. So we'll compile. Start simulation. Why can't it start up will not such element in that? Not happening. Please just the folder. It's here. Paste. Yes. So the problem I'll just tell you. So once we compile, we make sure that the design to be run for 1000 microseconds. So that is what one thing we need to understand. So we should make sure how much is the finish line is there. So we need to run it till there, and then we need to observe it. So that is what the coverages, you can see it here. So we have the statements coverage, everything, right? So I hope the coverage why it was less is because we have not run till 1000 microseconds. So once we make sure that our design, whatever we have designed, so it has to run till that simulation time, then the coverages are done. So you can see here the coverage for count, okay, with respect to your statement coverage, it is around 96%, and then there are few statements missed also. How many statements count and hit and then missed values. So all these things are available here. And then same way for your branch coverage. So it is almost 100% branch coverage. So we have 2 branch counts and 2 hits and 0 missed out of that. So like that. So we have toggle hits also. Toggles also, the values of reset and clock we have achieved. So that's why the toggle coverage is also 100%. So if you want any other coverages, so you can enable accordingly. I hope this is clear. So only thing, make sure that whenever the coverage you are planning, so initially it will be in uncovered state and run till the simulation value, how much in your code you are adding finish value. So this finish is not covered. So once I'll just make sure that the design comes with the finish value also, that can also be run. I'll just run one more time. So it will come out. So whenever we run till that value, so the simulation will run and then it will come out. So you can invoke your simulator once again, and then you can have same designs to be built. Any design you added to your project, so you make sure that you have configuring your compile with respect to the coverages here, these options. And after that, so make sure that you are going to start the simulation. So make sure that you select both the files of your design and enable code coverage and run it. Only these steps you have to follow. Initially now it is an uncovered state. So make sure that you run it till what the values you have specified. So I'll just running it for 1000 microseconds, so that whatever the coverages are will appear here, and those details you can find it here. So I hope this is clear to all of you. Yeah, just I already explained, right? So regarding coverage report. So I just select. If you want in terms of the report, I can take. So view the code coverage report. Can view it. So it's not there. I'll just a minute. Here only I'll get. So I'll just take the report in the notepad. You can find it here. So how many branches, coverage, conditional coverage, statement coverage, and toggles. So how many are there? That statements, how much it is covered under your .v file, and test.v file are available. And then overall, with both .v and underscore test.v file, we could able to achieve 96% of your coverage value. I hope this is clear. Yes, so whenever, not about an industry, whenever you talk about any your RTL design and make your design to be error free, and then whether you are covering all the possible values of test cases, okay, then it is mandatory. I hope I am answered your question, Dinesh. Anything else? So any questions from the audience? So these are the two ways. So you can either do it with your Vivado Flow or with PistaSim. So it is left to you to decide upon the same. So officially, we are winding up for the day. with the code coverages. So Prakash will address you regarding any queries or other things.
Hi, good evening to all of you. I hope the first day was useful to you. Chipin team, we have shared one feedback form in the chat box. So I request all of you to please fill out the feedback form. Okay, it's very essential for us.
Sure, sure, sir.
Okay.
So this PPT we can share it. Okay.
Right. Okay. Any questions are there?
For PPT, can we share?
I'll just discuss and let you know, because generally it's when we are recording the sessions, we don't share the PPTs. That's one thing.
Okay, fine.
Right. So because you're already recording the sessions for this, right?
Yes, yes, sir.
Okay. So any questions apart from this?
No questions, sir. Until now,
Don't worry about the
people are
PPTs.
asking. Yeah, people are asking about the material and PPTs.
Okay, see, you should not be worrying about the materials. You should be worrying about the content of the session. That's very important for us, right? So PPT, anybody can make it. A lot of various ways of things are available, right?
Yeah, sure, sir.
So we'll have the tomorrow session starting at 10 a.m.
Right. So tomorrow it will be covered by Asha, Chipin team. Okay.
Okay,
And
okay, sir.
I'll be there. I'll be there, part of it. Okay. And if time permits, we'll check it out how to. If already people have downloaded the software, how to install the software. That also I'll cover up in tomorrow or day after tomorrow sessions. We
Yeah,
have time.
people were saying like it is consuming a huge space, approx. I
Obviously,
think.
see, that's one thing already we have informed to most of the people here. Okay, so it will be the downloading file size is around 108 GB. Okay, and when you install it, it will take somewhere around 200 to 300 GB. So
200 GB.
make
Correct.
sure that you have that much space for that. Okay.
So adding upon what Prakash said, while installing the tool, there is one Alveo card, I think, which is comes under like accelerator. That portion, if you skip it for the installation, it will almost 25 to 30 GB only for downloading. Installation disk space, maybe it required around 50 to 60 GB for that.
So downloading file is required, but installing installation is taken. So while installing may not be required to select all the things. So some things we can reduce it so that your space consumption will be reduced for you. Okay. Am I clear?
Yes, correct, sir.
Okay, we'll wind up the things.
Yeah.
Any questions?
No, sir. No questions from our side. Thank you, sir. Thank you, Prakash, sir. Thank you, Manjuna, sir, for today's session. Thank you, sir.
Thank you.